This conference will now be recorded.
You're gonna do more than bang a gavel.
Welcome everyone to the TAC meeting for October, for the fall TAC meeting. Have a number of good talks this morning, and I hope you all enjoy them. So Maya is gonna lead those presentations.
Do y'all wanna do introductions? There's some new folks in the room. Start with Ryan.
Oh yeah, hi, I'm Ryan Moyer. I'm a co-chair of the TAC, and I think Kelly is online. I'm gonna do online introduction.
I don't even know if we need to do. Okay. We'll figure it out. I'm Maya Berg. I'm the assistant director of the Tampa Fishery Program.
I'm Mark Schremek, work with NOAA National Marine Fisheries Service. Good morning.
I work for the City of St. Pete. Sarah Herndon, Tampa Bay Watch.
Vicki Parsons, Bay Soundings.
Ian Paul, Tampa Audubon.
Chris Anastasio, Swift Mud Swim Program.
Christine Joyner, Pinellas County Environmental Management. Sarah Napier, Pinellas County Environmental.
Project. We can't hear you guys.
Oh, okay, yeah, I'm loud. Green One, USF. Kendall Benson, also USF.
Maya Breitbart, USF.
Jackie Champion, FDAX.
Sophia Gutierrez, USF.
Libby Rocker,
Dignat Rueda, USF. Julie Christian, Environmental Protection Commission of Hillsborough County.
Recently retired from the County.
Jillian Polino, a fellow with the Tampa Bay Regional Planning Council.
Marcus Beck, TBEP.
Sheila Scalaro, Tampa Bay Estuary Program.
Carrie Clardy, Tampa Bay Estuary Program.
I'm going to say we have about 40 people online. So welcome to all of you online. Be looking to hear us. We'll monitor the chat if there are any issues that arise, but I don't think we need to run through everybody that's on there, if that's all right with the group. Brian, do you want to introduce our first?
Sure. Our first speakers are Bob Ellis and Lindsay Hubner from FWC, and they'll be speaking about tropicalization of hard bottoms in the nearshore Gulf of Mexico.
Hello, everyone. Good morning. Thanks, Ryan. Thanks, everyone, for thanks to you guys for having us here today this morning. We're here to talk about a project that a couple of us over at FWRI have been working on for the last few years. The more recent focus of the project has turned to tropicalization of hard bottom habitats, but you'll see that's not how the project initiated. I will give a caveat here at the beginning that this is we're kind of still working on this project. We don't have, it's not complete yet. And Lindsay and I are going to try to hand this presentation back and forth. And we've never presented about this project formally before, so please bear with us as we go through it. All right, next slide, please. I'm going to try to give an introduction where I'm going to basically present the habitat and then talk about some of the concepts behind the project that we're working on. So we are focusing on the hard bottom ledge habitat that exists along the central West Florida shelf. Hard bottom habitats are basically limestone ridges that are believed to be relic shorelines. So at one point when the sea level was lower, these were coral reefs, and then as the sea level rose, they became buried, perhaps by sediment. The corals all died, then they get exposed, and they create these, really 1 to 6 foot tall ridges in the bottom. They're linear features. They tend to run north-south, but as shorelines do, they meander quite a bit. On the low side of the ledge is sandy habitat, and the high side is the exposed limestone, and that gets colonized by a suite of benthic invertebrates. These exist as one of the highest relief of the natural hard substrate habitats that we have along the West Florida Shelf. And as such, they serve as kind of these kind of oases in these sandy, flat bottom habitats. So they get colonized by lots of invertebrates, and lots of fish use them for habitats. Interestingly, this region and these habitats are generally understudied relative to other parts in the Gulf of Mexico. Despite them being pretty much right there in our backyard. Obviously, they're really popular in the fishing community. Pretty much every angler knows what you're talking about when you start talking about a hard bottom ledge. But from the scientific point of view, it's rather sparse, the information that's available for them. Next slide, please. So zooming out a little bit from the hard bottom ledge itself, looking at the region in general, Tampa Bay kind of exists in this interesting biogeographical location where we are in a transition zone between the tropical North Atlantic province and the temperate North Atlantic province. So it's thought that some past research has suggested that this has something to do with the geomorphology of the area. And there's been a lot of studies looking at the benthic communities and how they differ. So a recent study suggested that kind of came up with this map here that's on the slide, where you have kind of Pinellas and north, you have one suite of benthic communities, and then south, Manatee, Sarasota area, you have another. And so there we are right in that transition zone between these ecoregions. And for our purposes, this like ecoregion idea really drives the community character, the communities that we're finding out there. So generally you can think of the things in purple to the south as kind of this Floridian or tropical sort of, you find more of the tropical sort of species, and then the blue region you find these northern sort of species. Because the Gulf of Mexico is the Gulf of Mexico, it actually has a slightly different community composition than on the Atlantic side of Florida. So we actually have a special ecoregion for the northern Gulf of Mexico, this Louisianan. And then southern Florida has to be special too. So we have this sort of Floridian, tropical-ish suite of species that tend to be represented by that ecoregion. So all that being said, we exist in a transition zone. And that makes this a really interesting place to do some ecological, to study the ecology of the communities that we find. Next slide, please. So I said the word community a bunch of times. Don't worry about this slide too much. But basically, when we're thinking about community in the context of this transition zone, we really need to think about, when we go out there and we do a fish count or we do a benthic survey, the things that we find are going to be, the animals that we find are going to be created, this community is going to be created basically as this plus, you have to have supply, you have to have animals showing up, and then some of those animals will be lost, whether that's because they leave, they get outcompeted, they can't survive from the environment, perhaps there's disease that occurs, things like that. So the community that's present is really this, it's integrating all of these different processes that happen on vastly different timescales. But the main point is that we have to have supply, we have to have animals coming in. If we're thinking about tropicalization as new animals showing up, we have to have the ability for them to show up, and then we have to have the ability for them to persist. So they have to be able to overcome all those things in the loss column in order for us to see them over time. Next slide, please. Whoops, that's an old version. Didn't get the citations in there. So in terms of supply, we have two main processes by which we could get new recruits, new fish, or new invertebrates coming in to the West Florida Shelf. We have the loop current, which hopefully everyone's familiar with. It comes up through next to the Yucatan Peninsula, does a big kind of 180-degree turn there in the middle Gulf of Mexico, and then comes out along South Florida, between South Florida and Cuba as the Florida current. The map there, the colorful map, is actually showing some drifter data, and you can see that this is the loop. This is one example, but here's the loop current coming up through into the Gulf of Mexico, turning around, and then that's surface current pushing water onto the West Florida shelf. So we have the ability to get tropical settlers from the Caribbean Sea onto the West Florida shelf. We also have, during the summertime, the coastal currents tend to run from south to north along the coast of Florida. So we have a way to get some of those Floridian species moving north along the West Florida shelf during the summer. So we have a situation where we have the ability for tropical species to arrive in this region. Next slide, please. So here's what we're looking at. I tried to overlay this, kind of theoretical transition zone. This, of course, it's not going to be a line, but we might have this line where we have one community dominated to the south, one to the north. And then these are the sites that we're looking at for this project, and we spread across that line. And so our question then, if you go to the next slide, is that line moving north? So this idea that we would have these Floridian or more tropical species showing up to this region and then being able to persist in the communities would effectively drive that transition zone north. Next slide, please. So one of those factors that I didn't really mention that shapes communities, of course, is disturbance. The main disturbance that we have here in the offshore environment are harmful algal blooms. So we had a major red tide in 2005. We had another one in 2018. And these have the ability to completely reset these communities. In terms of the fish, that's my focus. I'm a fish biologist. Anything that can move tends to move out of the way, and anything that can't tends to die when these blooms happen. So this has the effect of being able to completely reset the community, and then the newer community that's going to replace what was there before is going to be really a function of supply, and then whoever can outcompete and outpredate whoever else shows up. So the research that we're doing, actually, I mentioned at the beginning, it didn't start out as with a focus on tropicalization. After the 2005 red tide, the FWRI Coral Group, along with some partners over at NOAA and elsewhere, did an assessment, that blue box there that starts in 2007, did a benthic community assessment to see how some of these nearshore hard bottom ledge communities fared after that 2005 red tide. So they went out and they assessed the coral and the benthic communities to see how they were recovering from that red tide. And so some of the FWRI Coral team had the idea to do a reassessment of that 10 years after that 2007 assessment. The idea was to go out, replicate it, see, all right, we got 2 years after the red tide, or 1 year after the conclusion of the red tide, we went out and looked, let's do it again 10 years later. Happened to be more like 11 years because of logistical factors. They reached out to me as a fish biologist. We said, hey, let's add fish communities onto this. We went out, we started surveys in 2018. We did about 4 or 5 sites, and then bam, another red tide. So the focus kind of at the beginning of this was really focused on red tide because now we're doing basically the same sort of assessment again. How did this impact the fish in the benthic communities? Next slide, please. And then as we were doing this study, we started to realize, or we started to recognize that we're observing a lot of animals that we didn't have records of from some of this previous research. And so we were able to turn this into a more focused tropicalization study rather, to sort of focus a little bit more on those organisms that we were observing and documenting, but we weren't expecting to find there. And I'm going to turn this over to my colleague, Lindsay Hubner. She'll take over the next couple of slides.
Okay, can everybody hear me?
You can.
All right, excellent. So as Bob mentioned, we started to look a little bit more at this tropicalization idea of these ledges on the West Florida shelf. And this was really driven by our observation of these cleaner shrimp and their anemone hosts. So these are very common symbioses in tropical coral reef systems throughout the Caribbean and in South Florida and the Florida Keys. So this shrimp, Ancylomys petersoni, is the cleaner shrimp, which means it removes parasites from fishes and as well can aid in wound healing on fish. And it is an obligate anemone associate, which means that it lives its entire life associated with sea anemones, primarily the corkscrew sea anemone, Bartholomew annulata, which you see in the photo on the right, and as well the giant sea anemone, Condylactis gigantea, which is on the bottom. That's actually a bleaching sea gigantea in that photo. And we observed all three of these organisms in our benthic surveys in 2018 and 2019. So we were wondering, how prevalent are these cleaning stations on the ledges that we're looking at, and what fish are they cleaning? So if these are primarily supposed to be tropical symbioses, are these cleaning stations that we're finding on these ledges, is it really only the more tropical or Floridian fish species visiting these cleaning stations, or maybe more of the temperate fish finding these cleaning stations and visiting them? So what's really kind of happening at this transition area between the two different ecoregions, and how is this symbiosis sort of playing into the community? Next slide, please. So as Bob mentioned, we surveyed at these 15 different ledge sites. They were sort of arranged into 5 east-west transects, and in each one of these east-west transects, there are 3 different sites that have different depth profiles. So at about 10, 20, and 30 meters deep, moving east to west, starting in about Clearwater, moving all the way down to Anna Maria. At each one of these sites, we did about 2 to 4 RVC surveys. And that's what Bob did. Those are the fish reef visual census surveys. I'm not the fish person. So that's where they would count all the fish in a cylinder and then, get an abundance estimate as well of the different species. I conducted the shrimp and anemone surveys. So that's the image that you can see sort of along the right there. We ran a transect for 50 meters along the edge of each ledge, and then I counted all the shrimp and anemones that I found and how they were associated as together into communities of cleaning stations along the length of the ledge. And then Bob's RVC surveys were as well at different points along the ledge, both on top of the hard bottom part of the ledge and as well the sandy bottom part of the ledge. And then at a subset of these sites, we dropped video cameras, GoPro cameras, at some of the cleaning stations that I identified in my surveys to get an idea of what fish were visiting these cleaning stations. So these were mostly our deeper sites where the cleaning stations were more prevalent. And so these were 2 dives for us to do these sites. So they were in about 70 to 90 feet of water. And so during the first dive, we'd find some cleaning stations, we'd set up some cameras to video them, and then we'd go up for our surface interval and we'd video each station for about an hour, and then we'd come back down and pick up the camera. Next slide, please. So now I'm going to pass it back to Bob for some of the fish results.
Okay, so overall, we counted a whole lot of fish. As Lindsay said, these are the standard reef visual census that's used pretty much throughout South Florida. We kind of modified it a little bit because the ledge habitat is a little bit different from the coral reef habitat that it was designed for. So as she mentioned, I set it up so that the cylinder that we count all the fish within is a 5 meter radius cylinder, and that would encompass the ledge through the middle of the cylinder. So we would get both sides of the ledge counted. In total, nearly 12,000 fish individuals that we counted across 80 different species. When we ran some of the initial preliminary analysis, found that they were most strongly sorted by depth. We expected to see a stronger pattern in terms of that north-south latitudinal gradient, but that really didn't show up. That's really, the fish communities really seem to be driven by depth, and that's what you can see in that NMDS plot. Those 3 circles there are the centroids, with the center being the mean for each of the shallow, mid, depth, and deep sites. In terms of some of the tropical species that we saw, we started to see some grunt species, schoolmasters, a snapper, 4-eyed butterfly fish, some parrotfish and wrasse that are more typically associated with the Floridian fish community group. I think in terms of the fish, the more interesting part of this is that we started observing adults of some of these species. And so if you remember that sort of supply idea that I was talking about, it's not uncommon for these things to show up during the summer. So having these animals, having these species appear and be observed and counted is not unusual, but what is kind of the more interesting part is when you start counting adults. And so those 3 species there on the bottom all have dimorphic adult versus juvenile stages, so they're very easy to tell apart. And when we start seeing adults of those, that's suggesting that those individuals are able to persist now in the community, and that's a sort of the second step towards in that tropicalization idea that's happening. So we started to observe that as the study went on. We have an increasing number of adults of some of these Floridian species that we're encountering. Next slide, please. And back to Lindsay.
All right, so these are some of the results from our cleaning station surveys, which took place in just 2021 and 2022. And what we found is that we found these cleaning stations with the cleaner shrimp at all 15 of our sites. And so I just averaged just the number we found per site across the 2 years, and those are the white numbers, is the average cleaner shrimp per site. So that was really interesting. I probably wasn't really expecting them at some of the more near shore sites, which tend to get a little cooler in the winter, and then obviously the more further north sites that are in the more northern Gulf of Mexico ecoregion, but they're across all sites. But what is unexpected, and this definitely threw me for a loop during the first year of the surveys, is that I was finding these cleaner shrimp not associated with sea anemones. So that's the yellow numbers that you can see there. And the sea anemones, Bartholomea, just showing here the C. gigantea, were very rare, so there's not really a lot to show there. That the Bartholomea are sort of sifting across the ecoregion. So we didn't find any of these sea anemones north in the northern Gulf of Mexico ecoregion. We also didn't find them at the shallower sites, which tend to get cooler in the winter, the shallower nearshore sites, but they were further south and deeper. And this is a really interesting finding because these cleaner shrimp are supposed to be obligate anemone associates, which means they're supposed to only be found on sea anemones. So what might be going on here, we think, is a possible mismatched range expansion or thermal tolerance threshold where there is sufficient, outside of sea anemones, there's sufficient habitat for these cleaner shrimp, and there must be, sufficient fish visiting their cleaning stations for them to persist, even though their host sea anemones can't persist or haven't expanded their range yet to the more northern or more shallow sites. Next slide, please. And so what this looks like, because we're finding these cleaner shrimp without sea anemones, we're instead finding them on a bunch of different things or just nothing at all. So in the bottom sort of two images on the left, a lot of the shrimp I was just finding just sort of hanging out in the sand, which is highly unusual. Or sometimes they would pick different sort of features on the bottom, like that tunicate in the middle top image, dislodged octocoral, like in that middle bottom image, dislodged sponges on the top right image, or just little bits of shell or sand fragments. And this is a strategy that's seen in other cleaner shrimp or cleaner fish species that tend to pick sort of landmarks, it's called in the literature, for fish to find them. And they center their cleaning stations around those landmarks. So we're possibly seeing a difference or a shift in behavior of these cleaner shrimp in the absence of their sea anemones as they are sort of potentially invading new habitats in the Gulf of Mexico. Next slide, please. All right, I'm going to pass it back to Bob.
Just to kind of wrap up, basically, when we did our study, you know, again, we started it for a different sort of reason, but as we're out there, we're finding that these sort of Floridian, more tropical associated species, we found them pretty much throughout the study area, and those included both fish and some of the benthic invertebrates. Again, we're not just seeing new settlers or recruits, which is somewhat typical because we do have steady supply that happens during the summer, but typically those we would expect that the waters would cool enough in the wintertime and those species wouldn't be able to persist. However, now we're seeing that adults are being established in these communities. We observed functional cleaning stations across the study area. This part is again ongoing. It takes a very long time to watch some of these videos and really try to identify the different fish that are showing up there. So we're still working on that. But we do have records that we have fish visiting cleaning stations, visiting and being cleaned by these cleaner shrimp, basically across the entire study zone. And so, you know, it might be possible that this kind of, we're already seeing that theoretical line has already moved to the north somewhat. And so that we're already seeing these effects of that kind of tropicalization. We collected, the last summer we were out, we collected a bunch of shrimp and we snipped some anemone tentacles, and we are currently wrapping up the genetic analysis of those to try to determine which route those might be coming from, either through the Caribbean or up the coast from the Florida Keys. We're also looking to compare those shrimp that we collected from anemones versus ones that were kind of out by themselves to see if there's any difference there between those two species, between those different behavioral groups. And yeah, hopefully we'll have a paper here one day, and maybe a more practiced presentation in the future. But that's pretty much it. Next slide, please. Work like this takes a whole lot of people. So here's a non-exhaustive list of people that helped us out, counting fish or shrimp, or laying out transect lines, picking up cameras, things like that. And of course, our funding sources, which this was all funded by the Fish and Wildlife Foundation of Florida, and with some support from the Sport Fish Restoration Fund as well. And that's it. We're happy to take any questions from the audience.
Well, Bob and Lindsay, I think you did great for not having a practice presentation, and I thank you for humoring me and presenting sort of an early look at this work. That's sort of a theme for what I've invited in terms of speakers to this meeting, because I think we're sort of starting to observe some new things, and it's really useful for us to talk early in the early phases of projects and sort of get to thinking. And so part of the reason, just for your information, if I didn't really explain this to you when I extended the invitation, is that anecdotally we've been hearing reports of people observing, you know, tropicalization, if that's what you want to call it, of our hard bottom in Tampa Bay, and we don't really have sort of systematic evidence of that. And so what we've been thinking about at the estuary program is, we went through these iterative mapping efforts with the Southwest Florida Water Management District and the Pinellas County folks. And so we think we've mapped the majority of the hard bottom habitats that are present in the bay. But what we haven't done is like work that's similar to what EPC did in the early 90s, sort of looking at the benthic fauna in those hard bottom communities and sort of tracking how those communities might be changing over time. And so we're thinking about sort of the next steps of understanding hard bottom habitats in Tampa Bay, getting to that finer scale look. And of course, some of what's on our mind is the questions we get from the media and the public in terms of what we're observing down in the South Florida, in the Florida Keys, in the reef systems, that folks want to know, if we're seeing any kind of similar effects, or if we're a winner in those kinds of temperature changes that we're starting to see. So those are some of the reasons we're thinking about this work. And so I just really appreciate y'all giving us that sneak peek of what you all were observing out there in the more offshore areas of the Gulf of Mexico, because I think it's useful context. So are there any questions online or in the room for Bob and Lindsay? So Julie,
Can I talk to you and
well, I think project your voice and we'll ask if they can hear.
awesome presentation. Thank you so much. Can you hear me?
And did you hear Julie?
Yeah, we can hear you.
Okay, this is a question, it's super interesting, but my question was about the shrimp. So can the little shrimp travel during hurricanes? And if yes, do we think that that is a possible conduit for moving species north as storms become more frequent and stronger?
I don't know if like the adult shrimp would travel during hurricanes. They tend to sort of tuck into, well, from my background, I actually did my master's thesis on this cleaning symbiosis in the Virgin Islands. And from my observations and from the literature, the cleaner shrimp will tuck into the holes in which the anemone is situated. And so they kind of just bed down and kind of disappear during rough weather. So I don't know if they would necessarily get transported. I think they probably arrived to the West Florida shelf via larval dispersal. That said, these organisms only live like a couple years. So what we're probably looking at is either they're continuously arriving or their populations are established enough on the West Florida shelf that they're self-seeding. And I think that hopefully we'll be able to find a little bit more information about that from the genetic results, what their relatedness is to other populations, if there is any. So that's the shrimp. The sea anemone Bartholomea actually individuals only live about a year. So that question is even, I think, a little more interesting, is are we getting new individuals from source populations outside of the Gulf of Mexico on a yearly basis? Or are they self-seeding as well? And some of the genetic information from C. gigantea that was done by Nancy Sheridan at FWC, I think she might actually be on the call, she showed that there's some inbreeding in the populations of the C. gigantea anemone in the eastern Gulf of Mexico. So it might not be as connected. This region might not be as connected to tropical systems as as on like an annual basis. I'm not sure if that answered your question.
She's nodding yes.
Yes. Good job.
Yeah, I got kind of a follow-on to that. I'm thinking causality as well, and it seems like temperature is really the limiting factor here, but kind of along the same lines, with respect to like maybe more long-term changes in circulation patterns, especially like those longshore currents along the coast of Florida, but even shifts in the Gulf Loop current. Is there any potential in that maybe some of those more kind of long-term changes could be also causing some of this dispersal and maybe help explain that disconnect between the anemones and the shrimp.
I think that's certainly possible. I don't unfortunately know off the top of my head what the difference in their sort of larval dispersal time is. So that would certainly potentially explain why, you know, we're seeing shrimp in areas where we're not seeing anemones. But yeah, I think, and then the temperature is an important factor as well. We did deploy temperature loggers at all of these sites for 2 years. We haven't looked through those data yet. I mean, I have just sort of casually from a coral perspective, and only the very furthest north 2 sites actually got cool enough in temperature profiles to sort of approach that threat level for stony coral or scleractinian coral cold temperature stress. And so the majority of these sites, at least from a coral perspective, are actually livable, at least in the 2 years that we had temperature loggers out there for stony corals, which are most of which are tropical species. So with that in mind, you know, I think it's certainly possible that other tropical organisms can persist. As Bob said, seeing in the fish community, just based on the temperature profiles alone, once their dispersal patterns are bringing them to these habitats.
Julie.
This is a question more for Bob. With the fish species that you were seeing, were there any that you might be concerned about already with sort of a competition issue with other species that are already here and established?
I would say probably not really. You know, because we're kind of in this we're already in this transition zone. I don't want to anthropomorphize, but these species are kind of used to each other. Most likely, they're used to encountering each other. One to think about, and this is more, you know, everything that I do has to be applied to fisheries. So the one that pops to mind is like black grouper and gag grouper, where they are you know, congeners. They're very similar in their trophic ecology. Gag tend to be the temperate species, and black grouper tend to be the tropical species. But you also get plenty of each species traveling across that boundary. And then what you'll just see is over time, assuming that this pattern continues, is you'll just kind of see one become more abundant and the other one become less abundant. Because these are all native species that we're looking at, there isn't really much concern that, you know, one's going to replace another. This is sort of a typical thing that would happen a lot of the time. So it all just kind of depends on that context, right? If you're an angler, then you might care if one species gets replaced, but in the context of the kind of communities that are out there, I mean, the only one would be lionfish, and we know that lionfish do perfectly fine all the way up to the very northern Gulf of Mexico. So those are established, and there's not much we can do about that except for, you know, kill them at will. But I guess there's a damselfish. There's an introduced damselfish that is showing up in some of the coral regions in South Florida and like the Flower Garden banks, that, you know, could potentially pose a threat to some of the native species. But besides those real non-native invaders, this is, you know, we're really looking at kind of a natural process that likely happens a lot. We just happen to maybe be, when I say we, kind of, you know, humans are maybe accelerating this, something that naturally happens over a long time scale.
Maybe. Carrie.
Hey, Bob, this is Carrie. I know this is in the beginning stages of your work, but I was wondering if you've had a chance to look at some of the historical fish surveys in the area, for example, hourglass cruises and potentially some of the more recent, say bait fish cruises or CMAP cruises, video data to see how common some of these species are as juveniles coming into the area. I know you're seeing adults now, but it'd be interesting to see how often they were kind of, unintentional migrants in the past.
Yeah, absolutely. So the Hourglass Cruises is probably the best historical record of what kind of quote unquote should be here. The challenge, of course, becomes that they weren't doing underwater visual census on scuba. They were pulling trawls, and they actually did send out divers to spear some of the other fish that weren't coming up in the trawls. But the whole time I was making this, I kept trying to think of what we could tell you guys in terms how is this relevant to the estuary. And I think Maya, you mentioned that there might be some old DEP information about the benthic environment, benthic communities of the hard bottom. So the challenge there is that the historical record tends to use different methods, right? Like they used all these different methods to find it, and now we go out and we do these underwater visual census, and is that actually directly comparable? Maybe. So it kind of almost it becomes very, at least qualitatively, you can say like, oh yeah, these things, they found them here back in the 60s, and we're fine, but I don't have any quantified data for that, right? So one thing, as you mentioned, that we can look at is, do they report just seeing juveniles, or do they report seeing adults too? And so that's kind of why I'm making some of that distinction. The other bit that's challenging is that a lot of the West Florida shelf research tends to be punctuated by disturbance events. So just like in our case, a giant red tide is or say a giant oil spill, that all of a sudden is followed by funding and research into what's there. But what we're really missing is that, a more continuous record. So we kind of have, we have the Hourglass Cruises, we have some research after the 2005 red tide. We have here and there's a student who did a dissertation or a thesis about it, and you have to hunt down their thesis and you can look at it. But so I guess relevant to the Bay would be to, if you have that sort of data, to think very hard about how you can make it comparable, because yeah, that's a huge challenge for the piece that I'm doing, which is that, trying to say, okay, how are these fish communities changing over time? Because every time we look slightly different.
Well, Bob, I think what I'm thinking about is how do we do regular, hard bottom transect monitoring, or something like we do for seagrasses, or like we do for the critical coastal habitat assessment. Like, what is the appropriate method that we can reproduce? How frequently do we need to do that? And then how can we build that into our annual funding streams to support that kind of work, so we understand it? Because you're absolutely right that what's been done by DEP and the aquatic preserve is different than what EPC did, back in the 90s, which is different from the camera surveys that, we've done more recently. So, trying to routinize all of that, I think, is something that's of interest to the program. So maybe we talk more.
Absolutely.
All right. Well, thank y'all for giving us that peek. That was really interesting.
Our pleasure. Thanks for having us.
Thank you.
All right, thanks, Bob and Lindsay. Our next speakers are going to be, is it just Marcus?
It's just Marcus.
Just Marcus, okay.
Or
From the back, Sheila. Dr. Marcus Beck of the Tampa Bay Estuary Program, and his talk is called Hot and Fresh.
He's really proud of himself.
Be nervous, I'm gonna have to step away for the next hour, so I won't speaker for the end of your talk.
I was thinking it's been 3.5 years or so since I've given a talk to the PAC in person. So, chapter, very exciting. As kind of motivated by what Maya was saying about climate change themes and also along the theme of like first time talks. This is really taking a look at better understanding temperature stress primarily, but also other stressors like salinity changes and how they might be manifesting or affecting seagrasses in Tampa Bay. This was really motivated by, in part, the recent media coverage. We had a very hot summer, and that really kind of motivated at least my part of this, looking at the long-term data sets. But as we know, these changes have occurred for the last several decades. So we've been long thinking about these issues as alternative stressors, but more recently, just the conversation around climate change and its impacts on the Bay have really kind of pushed this work forward. So yeah, first time giving this talk, I'm looking for feedback from you all about how we might think about these data. Some of it is likely questionable, but it's sort of our first attempt to distill the historical data. Yeah, so this is the long-term seagrass, basically. We have the SwiftMud data on the top from the district going back to 1988. And then on the bottom, we have the annual transect monitoring data that we do, that we coordinate among our partners from 1998 to present. So the timescales are a little bit different, but the point is you can see basically the long-term recovery of seagrasses in the Bay. And then notably 2016 on, we see this decline in seagrasses. And so I hope many of you are aware of that change. This was also a big motivator for this work, understanding why this change has occurred recently and the potential for these other stressors like temperature to maybe being a part of this story. So I'll talk about two different things today. The first one, briefly, is going to be talking about this study that Sheila's spearheading, kind of a new look at getting some high resolution temporal data for temperature in Old Tampa Bay, because that is where we saw, or where we see on the top left there, right here, most loss in seagrasses. So we think there's something particularly special about Old Tampa Bay. So we're doing deployments there, and then the second part, the bulk of this talk, will be what has consumed me for the last couple of months, looking at historical data to try to tease apart what we can say with the existing data sets, and can we link it potentially to changes in seagrass. So yes, Sheila's stuff. So yeah, this again was kind of motivated by the long-term temperature increases, but even more so what happened this summer with the very kind of intense heat wave we saw. The main question of this work is basically in the summertime when we have these very high peaks in temperature, could this be contributing to seagrass loss or preventing the recovery of seagrass beds in Old Tampa Bay, again, where that being the most loss of seagrass we've seen in recent years. So two hypotheses are it's not affecting it, but alternative being, yes, there is a difference in temperature basically at sites where we see seagrasses and sites where there's no seagrasses. And this is just looking at essentially the last 2 years of data that we have for coverage in Old Tampa Bay. So 2020 compared to 2022. And what that means basically is they're out deploying hobo temperature loggers out in Old Tampa Bay. So continuous temperature measurements every 10 minutes. And where they're being deployed is going to be these areas in comparison of the 2020 to 2022 data. You can kind of see it in this map up here. There's areas where seagrass was lost between these 2 years and areas where it persisted. So they're deploying the loggers in these areas separately to see if there's a difference in the temperature signature there. They've been going out every 2 weeks doing this, so very busy. There was a whole story in the Tampa Bay Times about it, you probably saw it. And there's about 5 or 6 deployments per year. And each deployment is about a week or so. And then again, this covers the summer period. And so we have 1 year of data. This is going to be continued for the next 4 years, rather. It's a 5-year project. And we can't really say too much about the temperature data right now because it's just 1 year of data. It's not particularly telling. We have analyzed a little bit, but nothing really jumps out at us at this point. We're hoping with the additional years, we'll see some more interesting trends pop up, basically. So as I said, yes, very high quality data set. I'm not aware of any other data that we have in the region that are at this level of precision. We're getting temperature measurements every 10 minutes. And so this really gives us the ability to see if there's like spikes in temperature that are going to be like acute stressors, or maybe there's something about the diurnal variation that we don't get from other data sets that this data set can help us look at. Other things they're collecting are information about seagrass and macroalgae abundance, salinity measurements, water clarity, all sorts of great stuff. So we're excited about this project. It's going to continue on. And we do have preliminary data online you can view. This is basically just time series plots of the different deployments. And if you poke deeper in that repository, you can see some of the initial analyses. But I just wanted to explain this to you all, that this is something that we're looking at, and it's going to continue, so sort of stay tuned. And this is, again, one approach at getting at that bigger question of how is temperature potentially stressing seagrasses in Tampa Bay.
I just want to thank Roger, because this actually came out of the
Yes.
optical model and some of the subsequent questions that you had. So you sort of piloted the methods, and then we're trying to build and scale up that work. So I just want to thank you for those observations that work.
Can I ask a quick question? The temperature loggers, it looks like, where are they being placed? Is it, I don't know, is that like 6 inches above the substrate, or like 10 centimeters?
Yeah, so we screw basically like a RV anchor down into the sediment in areas where there's seagrasses. It's like in a large patch of seagrass. And then the eye you can see, that extends 10 centimeters.
Okay.
So the logger is just above, they're all like 10 centimeters above the sediment surface, so.
And then also we're measuring that depth too, right? Total depth?
Correct. Yeah. Water depth. But we're doing all of our sites that we're deploying at are, they're no deeper than 2 meters.
Right.
Yeah, so we stratified it, and we keep it pretty shallow.
Yeah, so 5, 6 loggers each deployment, again, 3 in seagrass, 3 in bare sediment. And those sites are chosen randomly based on where the seagrass was lost from 2020 to 22 and where it persisted.
Awesome.
A lot of good work there. Any other questions about that before I talk about my desktop analysis?
Yeah, like for example, now that you have 1 year of data, maybe you can try to compare it with satellite data, sea surface temperature, days, sea surface temperature, night sea surface temperature, just to see if there is some kind of pattern around there, and if it can be related.
Yeah, that's possible, but it's, well, like any data set, there's caveats, so like it's in shallow depths. So I don't know if
yes,
satellite
it
data,
is,
for
and because
example-
it's shallow depth, you need the big picture of what is happening in the whole bay. So it is something that it is not that difficult to do. I mean, to get those images and then trying to see, if it follows a pattern inside the bay.
Yeah, and we've had a lot of discussions about the middle of the bay versus the shallow. There's probably likely different trends going on there, and what types of data sets we can use to answer the question of where and when seagrasses might be stressed by temperature.
Yeah.
So we're looking at all the data sets we have. Satellite data terrifies me, so I haven't looked at it. Is it?
I sent it to you.
Oh, yeah, the NOAA, yes, okay.
Before you guys move on, you're saying in the seagrass you're putting it, about what abundances roughly?
It ranges, which is why we're including that information. So yeah, we've had places where seagrass is present, but it's pretty sparse. But again, yeah, we're just documenting that. So potentially once we have more temperature data, maybe we can tease out some of those like brown blanquet abundances.
When we piloted this last year, it was much harder because the data were older. They were from the 2020 mapping assessment. And so we've been much more successful this year. So like we were taking very sparse seagrass sites that first year. But this year we were able to, I mean, yes, it varied, but we're deploying in nice lush meadows as well as totally bare areas, so.
Is your site selection, Sheila, is it species specific or is it just based on?
No, it's just based on your maps. Yeah.
I just want to add that I'm doing similar measurements of North Shore Park, and they're also on very shallow waters, the sensors, and I have one sensor in a Syringodium bed and another sensor in a mixed bed with the Thalassia syringodium. And then I've got two more sensors further out, which are, one is in area there used to be grass, there's no grass now, and then in another deeper Syringodium bed. So it's similar, except I just leave my sensors. They've been going for almost 2 years now. And so I just go out and check them now and then change batteries.
But you're not taking yours out, right?
No.
Okay.
Well, I take them out and clean them. I have like spare sensors that I take them, and replace them and take them home, clean them, and then put them back out again.
How often are you like going out and cleaning them?
No, I don't think cleaning is a big deal with the temperature. The way I do it, I wrap a thin cloth, copper cloth around the sensors, and that keeps pretty much all the growth away from the sensors.
So we're looking at it on multiple fronts. I encourage you to check out the link there. You can see some interesting patterns. There's one extreme outlier that's right by the Bartow power plant, with very warm water there. And you can actually see the temperature change with the storm coming through, which is pretty cool on Idalia. Okay, so while Sheila's out in the field, I'm at my desk pouring through the decades of data we have available. This is, again, looking at it from multiple angles. And given the scale of these data, they're obviously not continuous, but they do cover a much longer time period. We can really ask these much more broader questions. So the goal of this is really to see what we can find essentially with these existing data sets. What are the trends over the last 50 years? Because we have EPC data, for example, going back to 1975 or so. Where are these changes in temperature most pronounced? I'm also looking at salinity. This is not necessarily the focus of Sheila's work, but it is something that I think is a stressor. It's changing over time. There might be co-occurring or sort of synergistically acting with temperature that is important to look at. And salinity is not something we have, as a program, traditionally talked about in terms of its long-term changes, but I do think it's really important when you think about seagrasses and how it's changing the base. So we'll talk about that. So describing the trends, how are they related to seagrasses? Mostly looking at the period of record where we have transect monitoring data going to 1998, and also comparing the time period of recovery to the period of loss from 2016 to present. And as I said, looking at the potential contribution of these stressors individually, but how they might be acting together, both temperature and salinity sort of jointly affecting seagrasses. So of course, this is obviously driven by changes in climate, I'll say it. This is weather data from Tampa International Airport, looking at the long-term precipitation changes or trends at the top. This is hydrologic load data, so what's actually entering the bay. We get that from Janicki Environmental. And this is standardized precipitation index, which is kind of a way to look at precipitation anomalies relative to sort of a baseline at zero. And so what you can see here is, like, in the last 10 years, we've got a lot of rain. Not really this last summer, but this could be further driving the salinity changes that we're looking at. And this, of course, is air temperature from 1975 to present, and frankly terrifying. 2 degrees on average, or rather 2 degrees increase on average from 1975 to present. So it is getting hotter, and we're noticing it. Now we're looking in the water column here. So this is long-term monitoring data from EPC, looking at water temperature on the top, salinity data on the bottom, top plot, bottom plot, and then also as measured in the top of the water column and bottom of the water column. This is broken up by the bay segments, Old Tampa Bay, Hillsborough, Middle, Lower Tampa Bay. And really it's just an average of all the monitoring stations in a bay segment within a year by location of sampling, and then plotting a trend line on there. So no fancy statistics, just looking at a linear trend in temperature by bay segment and salinity by bay segment. And very clearly an increase in temperature as suggested by the air temperature, and a decrease in salinity. Not quite as dramatic as temperature, but I believe it's still there. In particular, like Hillsborough Bay right here, we see generally lower salinity values below the trend line, and I think again that's a function of just the period of rain we've had in the last 5-10 years. So overall trends, the data don't lie, and I think this is pretty compelling.
So tell your friends and colleagues this, because the assumption is with sea level rise, the bay is going to get saltier. And so many of you are working in local governments and you have separate resiliency officers, and they continue to kind of say this. And we need to kind of like match this up with the data and what we're actually observing, so that that side of the house is evidence-based and that we can kind of like work together to understand these phenomena. So that's a take-home message for your colleagues.
So Marcus, so this is so cool. I have to say that out loud because there's so much going on here. Like it's incredible. Just so another thing to consider, because you got to bear circulation into this whole equation as well. And when you see that almost phase shift in Old Tampa Bay and Hillsborough Bay, what it tells me is that in recent times, when these bay segments get fresher, because there's more fresh water coming in, it stays there. So it stays fresher longer, which I think also has a major impact on this. And then you throw the temperature on there. Yeah, there's a lot going on.
Yeah, the variability between years, the confidence intervals, there's a lot you can spend on this plot. The other thing I'll say is this also is not intuitive. With a reduction in salinity, so more inflow basically, you would expect the temperature to decrease. That's sort of a typical phenomenon. It's there. A lot of inflow, water temperature decreases, but overall temperature is increasing. And what I think, and I'm just sort of guessing here, is I think this is a function of the watershed development we've seen in the last 50 years. A lot more paved surfaces that are really elevating the temperature of that water as it comes into the system. So that's why I think we're kind of seeing an opposite trend of more fresh water.
If you think of Old Tampa Bay, and maybe even Hillsborough Bay, but definitely Old Tampa Bay more as a lake than as a.
I do think of it.
Yeah, it kind of functions like.
And then you get a die off, and then you have, and it's
so that fresh water comes in. So I think it's both. I think you're right. The temperature of the water coming in is, and that would be really cool to be able to make that connection. But then it sits there.
The residence time. Yeah.
Yeah.
But you see, temperature trends are almost the same across all the bay segments. So, this, there's a lot of stuff going on here. Stacy.
Are y'all looking at depth? Like, is it possible that there's some sedimentation that's making the water shallower, and that could be causing increases in temperature?
Is the bay filling in? I haven't looked at that. That's a good story.
But that's part of why we picked those shallow seagrass beds. So we're trying not to get we're not doing the deep edge. We're trying to get those shallow areas. The idea that there's less thermal buffering going on.
And the loss that we've seen in places like Old Tampa Bay and Hillsborough don't suggest that it's a depth light issue, because it's not just the grass at the deep edge we're losing grass in shallow sounds too. Yeah.
Very shallow.
Very
That's where
shallow.
we've seen a lot of the loss in seagrass. Old Tampa Bay. Okay, Looking at the trends a little bit more, this is kind of the same thing, but using actual like trend tests. So Kendall trend tests basically shows what is the significance of the monotonic change from start to end of the record. And this is really just getting at more spatial resolution compared to the previous plot and what time of year you see those changes. So salinity, left column, temperature, right column, measurements in the top of the water column, measurements in the bottom of the water column. Again, telling us the same picture. Salinity is going down, temperature's going up. It tends to be a little bit more pronounced in the upper part of the bay, especially for salinity. And then this is the seasonality changes. So not only overall is it changing, but what time of year do we generally see these changes? And as you would expect, like for salinity, this happens more often in the wet season. So when most of the water is coming in, that's when we see these trends popping up to be more significant. Temperature as well, interestingly, and it does kind of vary by location in the bay. The closer you get to the upper part of the bay, it tends to have more of a seasonality to it. But again, this is another one of those plots you can look at and sort of hypothesize about what's happening, but I really just wanted to give a bigger or a deeper dive into like where these changes are happening, what time of year. Mostly just confirmatory with the previous. So where we're at, so that's like what is the trend over this like 50-year time period. Next, I tried to relate these changes to seagrass change to see if there's a potential relationship, and where this is my really stupid theoretical model where I tried to like understand where in this sort of optimal range we are. So there's like any organism, there's like a temperature range, and there's well, a salinity range too, if we're talking about coastal environments. And ideally, you know, their niche is going to be somewhere in the middle between like a low and high temperature and low and high salinity. Now, obviously, increasing temperature or decreasing temperature will force it out of that niche. Same for salinity, and these things can happen at the same time. So where I think we're going with the bay is this trend towards a condition for seagrasses where they're stressed by high temperature and stressed by low salinity. So that's kind of what I'm trying to quantify when I'm doing these analyses. There's certainly other ways we can look at it, but this was at least how I kind of conceptualized the approach. So what I did is for basically the EPC data, so 45 or so monitoring stations in the bay, monthly, 12 measurements a year, I wanted to take the monthly data and quantify each year what was a potential measure of thermal stress and what was a potential measure of salinity stress. Now, I could do that with the monthly data, but even better, we can fit these models to get a continuous time series for the whole record. We can actually break down on a daily scale to say, for example, how many days within a year was temperature above a particular threshold? And was that changing from 1975 to present? And the answer is yes, it was, but we can do these types of exercises with these models to quantify the stress at an individual station, both with temperature and salinity. And so salinity would be the opposite. So how many days in a year was salinity below a particular threshold? And we can pick these thresholds based on the literature. So we know, for example, like seagrasses might get stressed above 32 to 33 degrees, maybe higher than that. Varies by species, but we can quantify these stress metrics based on these thresholds that are peer-reviewed basically. So if that wasn't clear, this is again my schematic of how that's done. Theoretical temperature time series, theoretical salinity time series. We can pick the threshold, and so we could run this analysis iteratively to see which threshold is giving us the most sensitive relationship. But once we define that threshold, we can basically say each year, so each hump is a year, seasonal change, how many days was temperature above that threshold in a year, and was that changing? And same for salinity, but reverse, because more fresher waters might be stressing the seagrasses. And we get metrics like this. So stress column on the left, and then within each year, we can count those number of days. And I think that's a better measure than just temperature alone, because again, it could be referenced by a threshold that could have some ecological meaning, and it's something that does change between years. That's just sort of a single metric of that stress. So this is what it looks like for the major bay segments for these thresholds. Oh, other thing too, in addition to just looking at the temperature stress and salinity stress, we can also measure times when both of those things occur. Times when both temperature is above the threshold and salinity is below the threshold, to get an idea of when they might be both stressed by these things together.
Marcus, maybe I missed it, but the data that you're using are point data. So when you're talking about number of days, these aren't continuous data.
They're modeled continuous days from the monthly EPC data.
Okay.
And these models have like R-squareds of like 0.99, so they're pretty good. But usually they do miss some peaks, which could be important.
Gotcha. Okay.
This is me for like weeks just trying to sort this out.
And this is like the best we can do when we don't have continuous water quality
Right.
monitoring stations in the building. So
Yeah.
if we need to start to make a case for that, okay, but for now.
Well, you know,
Marcus did build it in.
yeah, no, that's fine. I was just curious, like how you built the model, like it was based on.
It's just a nonlinear generalized additive model of temperature or salinity is a function of like decimal year.
And the salinity when, so I'm assuming this station is an EPC station?
Yep.
And
It's 66 in Old Tampa Bay, which is where we see a lot of the pyro blooms.
And are the salinities, I mean, are the data points collected irrespective of tide, or is that a concern? Like when that data point is collected? I guess that's
Yeah.
I don't know if that's as big of a difference, if that makes as big of a difference in Old Tampa Bay, but.
No, our sampling's not tide dependent in
okay.
any way.
There's a time of day component too, especially with temperature.
Yeah.
So,
And I think, you know, I think what you've got working for you though, is that because you're using such a long-term data set, that tends to wash out. Yeah.
One thing, you know, we do the exact same route every time we do our sampling. So, you know, with regards to time, every month we're probably hitting the stations around the same time, give or take, you know, half hour, an hour, because we do follow the exact same route. We're out, you know, every morning around the same time. So, you know, if we're normally sampling in the morning, then that station's normally always going to be sampled in the morning.
Okay.
Is that why the west side of the bay looks wonderful? Yeah, so there's limitations, but yeah, do what we can. And the value of this large data set is, like you said, I think some of these things do kind of come out in the wash. So this is just showing the quantification of those stresses at the bay segment scale. So I went through this exercise for every single station. So I had like, I don't know, 15 or so stations in Old Tampa Bay, similar amount Hillsborough Bay. And I fit these models and quantified the metric, and then fit a linear model to see how these stressor metrics were changing at the bay level or bay segment level. So each gray line is going to be a fit for an individual station, and then the solid colored lines are going to be the overall fit, where station is kind of like a random effect that is considered but combined when you're looking at the whole segment scale. So like, for example, if you're reading this, you could say, oh, and these are the thresholds I picked. So these aren't necessarily the most sensitive thresholds for like what's said in the literature. And this is where I kind of played around a lot with it. You know, we could use salinity less than 15 or temperature greater than 35, but these were the thresholds that gave me solid models here. And it does kind of speak to sort of the upper limit of these observations for the temperature. Like we don't see a lot of salinity values less than 15 in Middle Tampa Bay, for example. So you can't really fit the models with that type of threshold, even though that metric would be more of an indication of stress for seagrasses because it is lower. So anyway.
We have a question in the chat. I don't know if you want to take it now. I'll read it to you. It's from Dave Tomasco. He says, while salinities are decreasing, they do not appear to be below what are critical values for Haladuli, for instance. Although there's prior evidence of the adverse impacts of synergistic effects of decreasing temps and increasing salinities on die-offs of seagrasses, not sure if such a combination have been shown to be problematic in other areas. what is justification for threshold values for salinity stress?
I just answered that, Dave. Really not much. We tried to, go ahead, Dave.
Well, and what I was wondering is, and I mean this in the best possible way, but it almost looks like you're looking for a salinity that's stressful to explain a decline rather than the literature suggesting that 20 salinity is not particularly problematic for haliduli, for example. And, I'm kind of wondering if like, and that kind of gets to the thing of like, certainly increased temperatures, increased salinities, Florida Bay die-off pops up, but increased temperatures and decreased salinities, I'm not sure how that has been explained in prior die-offs. And so I kind of think the temperature data are really impressive, but I'm not quite sure the salinity, I'm not convinced that the salinities are stressful even with an increase in temperature. They just don't seem to be deviating to like the range that I would think would be problematic for seagrass.
Yeah, and that's sort of the punchline of the end of this talk is I'm not against either, but there are some suggestions that it is like possibly playing a role, and it's very likely that we're not at a point where those thresholds have been exceeded at a level that's going to stress the seagrasses. And that, like, I would gladly use a much lower threshold for salinity, but like I said, you don't see those measurements as often, and therefore you don't get good stressor measurements, using that threshold.
Look, that I guess was my concern, is it almost looked like you're saying the salinity is stressful, and I'm meaning this in the best possible way, like you're saying this is a salinity that's stressful because it's exceeded this threshold level, when maybe it's not. It's just, this is kind of like a spurious, and I mean that in the best way, a spurious stress threshold.
Yeah, I agree. The choice of the thresholds is going to be something that needs to be better justified, but again, it is a limitation of just the observations of the data. I don't honestly think we're seeing salinity values that are going to be at a value that's going to be low enough to impact the seagrasses, at least using this approach.
And I apologize, I meant to be at this meeting, but I had something in Sarasota. I apologize, but in the temperature data set, it almost looked like a step change. There was no change in the locations of stations in the temperature data set in Old Tampa Bay and Hillsborough Bay, was there? I mean, that looks like a step change, not like a trend.
Yeah, and these are just linear models too. So I was just kind of trying to demonstrate with this that these are trends for the stressor, quote, stressor metrics. And when I actually use these in the models, I'm actually using the calculated estimates from the actual stations rather than the fit through all of them. So
thanks, Marcus.
Let me show you the models, and you could determine if they're BS or not. But what I tried to do was, again, take these stressor metrics and understand potentially how they're related to the seagrass change. But the problem with this is seagrass obviously has not increased or decreased monotonically throughout this period of record. It's improved or increased as the bay recovered up until about 2015 or so, when we saw this decline. So these stressor metrics are sort of continuously increasing. And so if we model this relative to seagrasses, it's going to show that there's a positive association of seagrass with stressor increases. So we got to be a little fancy with our models. And what I did was basically a linear model with these data, but I looked at the bay segment scale by year using the seagrass transect monitoring data, using frequency occurrence as a response measure, percent change between years. So if it went up 10%, down 20%, whatever, between years, and then just simply an increase, decrease binary from that. Now, the drivers of this model is these stressor metrics, both increasing salinity or decreasing salinity, increasing temp in both, as well as a categorical variable for bay segment. and a categorical variable for time period to account for that confounding relationship. So I had basically a variable that said, was this time prior to 2016 or was it 2016 and later, to show that, times when those relationships might change. So right off the bat, frequency occurrence, this is my model. Frequency occurrence did not show any relationship. Percent change in seagrass between years did, as well as the increase decrease as a logistic model. Temperature didn't show any relationships, neither did the both metric, but salinity shows some interesting patterns. So these are basically the predictions from this fitted model. And again, I didn't look at lower Tampa Bay because not really much is, the seagrasses are stable there. So I didn't consider it. And so we have basically this is two different models. On the left is percent change in seagrasses. The response on the right is the same thing, but yes, no, probability of seagrass declines, whether present or absent. And I have the model fit as a function of, on the x-axis, number of days salinity was less than that threshold, and categorical variables for bay segment and time period. So bay segment rows, time period columns. Not a lot of relationships here, but these two parts of the model, the fits for Hillsborough Bay and the most recent year, does show, at least in the percent change in seagrass, a negative association as that stressor metric increases over time in the latter period. And then this is sort of the same thing, but modeling the probability of that decline in a logistic model. So reading the tea leaves a little bit, this might suggest that in Hillsborough Bay, recently seagrasses are stressed by increased freshening. Not really sure. These are really poorly fit models, but just kind of throwing spaghetti at the wall, seeing what sticks. Using kind of a weighted evidence approach, I also wanted to look at alternative data sets. So all of that was EPC's data, using the transect monitoring data. We also have a lot of great data in the FIM monitoring data set from FWC. They've been going out for 3 decades or so. Lots of different type of data, lots of different sample points, not the same spot each time, but there's a lot of information when they get the fish. They look at seagrass presence, absence, also cover, temperature, salinity. They take all the same kinds of measurements. What I did with this data set was for each sample point, it's a different random point each time. I looked at, was seagrass there, presence, absence, what was the frequency occurrence of seagrass, and also looked at the measurements that were taken, as I said, salinity, temperature, where it was, and also where in the time period it fell. So was it prior to 2016 or after? Now, because this is a different data set, I cannot calculate these metrics of like number of days per year temperature goes above a threshold. It's just one point at one location. And they usually never go back to that point. But I can look at just observed salinity and temperature, and I can aggregate that at the bay segment scale. So the models are mostly the same. I just don't have the stressor metrics. I just have the measured salinity and temperature. And because this is a larger sample size, I can get fancy with the models and use nonlinear approaches to maybe try to describe the trends a little bit more. So these are my models. I did separate ones for salinity and temperature in this example, but I have interactions with bay segment and time of year to see if there's changes in the relationship based on those factors. And I looked at percent cover of seagrass and presence absence. So again, more spaghetti, but this is sort of the same setup where I do think, even though the models have a poor fit, there are some trends popping out that are of interest. So for example, last time, remember the story was kind of like Old Tampa Bay, how salinity was maybe associated with changes in seagrass there, or Hillsborough Bay rather. Here's kind of the opposite. I'm seeing associations in Old Tampa Bay and Middle Tampa Bay. And so here's salinity on this plot, seagrass percent cover. Looks like in the recent period of record, there is sort of a positive association of salinity with seagrass. So in other words, the less fresh it gets, the higher proportion of seagrass you see, higher cover of seagrass. This is what we would expect. So more freshening, less seagrass. Kind of the same for Middle Tampa Bay, sort of in the prior period, but maybe a little more pronounced in the latter period. And then finally, in Old Tampa Bay, this is the only model I had where there was maybe sort of an association with temperature. So this is the latter period, looking at increasing in temperature. We see sort of that slight but noticeable decrease in seagrass cover. So this is telling me that maybe something's going on. It's a different model, different data sets. I'm not surprised. I don't see the exact same thing. But using this similar approach, I am seeing some relationships that sort of make sense based on how I'm thinking about these stressors affecting seagrasses. So that's it for now. Again, open to discussion on how we might approach this further. But point is, these trends are very evident in the data in terms of increasing temperature, decreasing salinity. Our weight of evidence approach with these models do suggest some associations. They're weak. It does not rule out the potential for these stressors to really impact the seagrasses. It's just that, like we were talking about, we might not be at a point yet where we're seeing these changes fully pronounced because we're not necessarily really exceeding these thresholds, and they might be more pronounced in the future. Bigger picture though, nitrogen, that's going to be our bread and butter as a program for how we think about managing water quality for seagrasses in the bay. We're not departing from that. We're just trying to start a conversation around how these other stressors could be considered for a more holistic approach to managing multiple stressors that could be affecting seagrasses. So
You have a question online from Kara that's kind of touching at that. It's what about factors that may co-vary with salinity or temperature? For instance, high rainfall can bring both low salinity and higher nutrient input from runoff, which can drive phytoplankton blooms and decrease light availability for seagrass. Are you considering measuring other metrics as well?
yes, I tried throwing in nitrogen into these models and it just made it more confusing. But you're absolutely right, Kara. There's a lot of other factors that are driving seagrass change, and you throw all these data sets into a relatively simple model, it's just going to be really confusing to try to tease apart drivers when you have multiple predictors. So I'm open to like other modeling approaches that might tease this apart a little more clearly. And I do agree these other stressors must be considered to more sort of fully evaluate what's driving the changes.
Yeah, Chris.
Yeah, so I think that to Dave's point, I do agree with him that maybe we should try to stay away from looking at threshold values because it's the same criticism I give to TMDLs and numeric criteria. There's no magic number. And you don't want to get stuck focusing on a single number, even a range number. But what this definitely does is I think it puts this into this perspective of, and you said it best, so it's a weight of evidence approach. And so you're looking at a weight of evidence, and while these may not be stressors that have direct causality towards loss of seagrass, they certainly don't help. And so it's kind of like, I always use the medical analogy that, if you have high blood pressure, you got diabetes, and then you get COVID and die. Those factors may not have killed you, but they definitely didn't make it
comorbidities.
Comorbidity. Yeah, exactly. Sublethal stress is like, in the literature, what has typically been used to describe, kind of getting over. But I think another point too to this is that, and we don't really talk about this much because it's really hard to quantify, is the role that competition is playing here. So, this is kind of like, this is like a cage match, as Dave Tomasco puts it, between macroalgae and seagrass. And these factors might ever so subtly shift that competitive edge one way or the other. And so we have to remember that when we're looking at these analyses. And the most important thing, I think, for resource managers is not necessarily to look for that smoking gun that, oh, it's salinity or it's temperature, but that this analysis that Marcus is doing helps manage expectations. So absolutely, we need to reduce our nitrogen footprint. We got to go on a nitrogen diet, no doubt about it. But in a world where we have less salinity and higher temperatures, we need to manage the expectation that, okay, well, if I reduce my load by 20%, that's going to make everything better. Maybe now it's 30 or 40, we don't know, but it helps put that narrative in context. And I think that's where a lot of this work is going to hit, is to help us put this in context.
And that's a really good point. We talk about these other stressors, but what can we meaningfully do about them? So you can't throw ice cubes in the bay, or we can to an extent like manage flow, but we kind of make the bay more salty.
Yeah, and the managed flow is also gonna have a benefit for the nutrient load.
Right.
So, like these things, like it goes back to what are the actionable, that's always been as a program and with you all and our partners, like, yes, we have to have research and evidence, but it also has to be things we do something about. And that's sort of why we're up here throwing spaghetti with you. So we can all sort of agree on what that course is gonna go forward. Ping.
Okay, so nothing to do with the temperature, salinity, and the nutrients. Some question to all the seagrass expert here. If you see that sharp drop from 2016, 2017, 2018, we did get hit by a rather unusual hurricane, 2017, Irma, right? It drew all the water out, not all the water, really dropped the water level, make the wave very aggressively, physically can erode the seagrass. Has anybody looked at that? The impact of Hurricane Irma, physical forcing.
I believe Dave Tomasco has. Didn't he? Is there a paper that he published on that?
Yeah, we did. We looked at the trends in seagrass coverage after that decline. That decline's not found everywhere, for example. So that decline in seagrass isn't found in St. Joseph Sound. So the healthier parts of our west coast of Florida doesn't show the adverse impacts of Ian or Irma. But it does look like the places that were on edge lost most of it. So for example, in our area, lower Sarasota Bay was already losing seagrass, and it lost more after Irma came through. And in Tampa Bay, it looked like the same thing. The areas that were healthy weren't that adversely impacted by Irma, and they certainly weren't destroyed by the physical activity, because those two storms didn't bring a storm surge. They pulled water out of the bay. So I kind of think that
by pulling water out of the bay, that would make the wave forcing a lot more aggressive in terms of, so if you look at the impact, the wind would come at a certain direction. If you look at the wind, like at the wave inside the bay would be a function of the fetch, right? So not everywhere you would have big waves. If the wind is blowing from east to west, then the west side would have much bigger wave, then the east side would be sheltered with less wave. So, and anybody looked at basically the specifics of wave generation and the specific location of seagrass destruction? Just trying to learn here.
And I think to add to that, a lot of those marginal areas have very soft sediment, almost a muddy sand. And so that to me would also be more prone to those physical forces, because the roots, the rhizomes don't have that as much to hold on to. So when you get those like reverse surges, those areas are especially prone. I mean, anecdotally, for example, Hillsborough Bay, we did see a significant drop after Irma. I don't know if that's, there's many factors that could have contributed to that, but certainly that reverse surge, I was, friends were texting me pictures of them a quarter mile offshore of Bayshore Boulevard when Irma came through. So that certainly could have had an impact. And we did start to see a recovery after that, but then Piney Point happened. And
I just want to call everybody's attention on the screen, that stuff those trends were happening before Irma passed through. And so don't forget about Hermine, for example, and those extreme wet weather events we had in 2015 and 2016, which the mapping, the way that the mapping periods worked, you're only getting a limited amount of data that's actually showing what happened post Irma. We have, starting in 2015, we have seen that period of wetter weather. Like we had some real extreme events with extreme nutrient loads as a result of that. We've also seen construction activity in the Old Tampa Bay segment. So there's been active filling of bay bottom there for causeway construction, and that can have relationships to light attenuation as well. So I don't think we've done enough, as much as you probably would have wanted us to do to answer that question yet, Ping. I think it's like a fair topic for inquiry. But there's definitely a lot that's kind of gone on, and that's why we're at this spaghetti approach of confounding factors and, you know, what's playing the most prominent role. We've got two more questions in the chat. One's from Dave T, one's from Gerald. I'm going to start with Gerald. Have there been any trends in KD since seagrass decline started?
I'll let Roger answer that.
When I ran the models for between the 2016 and 2021, I think it was, I could not see any major changes compared to the earlier period. And when we had increases in seagrasses, just it didn't show up in the model. And I looked at the last year. There was a gap there during COVID. We didn't have enough information, but there hasn't changed much. It's pretty much been steady.
Yeah, and
Roger,
Yes.
this is Gerald. I was just sitting here playing with R and looking at some box plots for Old Tampa Bay, and it looks like since around 2012, 2013, there's been, at least what I'm seeing, this is real quick and dirty. I was doing this while Marcus was talking, but it looks like there is kind of a trend between 2013 and 2021, and it looks like the KD values are starting to creep up back to where they were around 28 to 2010, something like that. I don't know if there's anything there or not, but it just it looks like there may be a little bit of something going on, possibly.
The KD values.
Yeah, I was looking at the the TVEP estimated KDs based on the EPC SECI data.
Yeah, if you look at our water quality report card, you can see the light attenuation creeping up ever so slightly in Old Tampa Bay, and we've been talking about that for the last couple of years. It's something to keep an eye on. But
yeah, of course.
The last 2 years, it has improved a little bit. So again, it gets back to this idea that we don't necessarily think that water quality in terms of light attenuation is necessarily the only thing driving seagrass change in this basin.
Yeah. Sorry, Marcus. I should have looked at that first instead of sitting here playing around with R. Thanks.
Good. All good. I like the fact you're playing around in R.
Go ahead. I think Dave had put a point in here, just like reiterating some of these macroalgae pathways and how macroalgae can be a winner given these warmer and pressure kind of.
I'm curious to see that you have been seeing a declining trend in the salinity. And just anecdotally, when EPC did our transects this year in Old Tampa Bay, especially north of the Courtney Campbell, I saw more rupia than I've seen in the previous years. And I've always simplistically been taught that the rupia is the more fresher of the seagrass species. And so, I'll be curious to see if more people are seeing it in Hillsborough Bay, or if we're starting to see an increase of rupia if salinity is declining.
We saw it last week in Old Tampa Bay for sure.
We've also been seeing more prominent in some of our sites, and I don't know if that's like we're looking for it more, you know what I mean? But rupia, a lot of people, I mean, it is technically like a freshwater salve. But it also, you can find rupia in the Keys during hypersaline. So it's not just, like, it's got a really large range where it can withstand.
Yeah, we've been coaching folks more to look for rupia during the transect training. So we might just be seeing more because we're telling people to look for it. Definitely keep an eye on it.
Or we're getting better at identifying it,
One other thing to consider before we move on is, I don't have an answer, but when we're thinking about temperature and salinity, let's not forget the microbiological activities that are happening between the sediment water interface. There's a lot of action that's happening in the sediment, and we tend to focus so much on the water column, we forget A lot of what's happening is being driven by what's happening in the rhizomes in the sediment. So it's something else just to think about as we're looking at these data. We need more data. More data.
So in the vein, and if you all need to take a break, well, we can agree to take a break right now, or if you just want to step out as you need to, you're more than welcome to. Is there a consensus about how people want to proceed? All right, we're just going to keep rocking through it then. So, generally, I'm hoping you're kind of picking up on this theme of, we have a clear management paradigm for dealing with seagrasses, and it relates to the light environment, controlling nutrients so that you can decrease algae growth and you can support seagrasses. But, back in the early 2000s, I think there was a forum that Holly and others convened saying it's not just nutrients. And we're sort of like coming to that moment again, what's old is new again. And so we're trying to expand people's understanding about the processes that might be going on that are explaining these 3 successive periods of seagrass loss that we've observed in the bay. And so these physical stressors, these things related to temperature, and salinity are a part of that. And we have some potential follow-up questions that may come from this work on temperature in particular when it comes to the reproductive biology of seagrasses and how they may or may not be conserving energy in light of these high temperatures. And it maybe not causing the die-off, but maybe slowing their ability to recolonize. So we think that there's maybe successive work that needs to happen there. But another question, another example of this, what's old is new again, is what's the potential role, or like when we see mass die-offs, is it viruses? Is it something else? And so we have some older research, but we haven't really revisited these questions until now. So again, this is Maya being willing to come to us and talk about like the early stages of work she has planned, and just sort of also a refresher to get people up to speed on the state of knowledge for some of the viruses and other things, pathogens associated with seagrasses in Tampa Bay. So Maya Breitbart.
Thanks. It's always fun to not be the only Maya in the room. So that's a good one. Let me know if you're having any trouble hearing me. I'm actually kind of giving 2 talks today, one that I'm much more comfortable with than the other one, so you'll have to bear with me a little bit. Cliff Ross at the University of North Florida is really the expert on the labyrinthia, and he sent me these slides, and I'm going to do my best with them. And then I'll transition to some work that we're doing with viruses. Like Maya mentioned, it's very new work. I'm going to say it now, and I'm going to keep saying it throughout. We don't know that these are causing disease right now. And so, I think Chris kind of gave a great transition into, we should be thinking about the microbes, but not only thinking about the microbes as pathogens. So I'm going to start with Cliff's work on labyrinthia. And I'm going to go through these initial slides really quickly because you guys all know the state of seagrass in Florida much better than I do. But of course, we're having lots of losses. That's true in Tampa Bay as well as in Florida Bay. And in Florida Bay, his lab has done work with the large die-off in 2015 as well. So what you've heard a lot about, and I think what is often focused on, are the abiotic suspects that are involved in seagrass loss. So salinity, thermal stress, eutrophication, algal blooms, and the competition between algae and seagrass. Other things such as sulfide levels, hypoxia, and we know a lot less about disease. And as a little kind of background, and I've tried to throw some history in here because I was actually surprised to learn a lot of like the early history and then how there's kind of big gaps and then things coming kind of back around. But in the early 1930s, Zoster marina was really wiped out by a wasting disease, so seagrass wasting, along the Atlantic coast of North America and Europe, but they never clearly determined the cause of what was happening at that point, but had kind of some implications that it was a marine slime mold, labyrinthia. And then it wasn't until 1988 that there was a paper published where they actually fulfilled Kuh's postulates and showed that it was labyrinthia that was causing wasting disease in the seagrass. So that was, about a 50-year gap. And this is pretty common. Usually in disease response sort of things, we're behind the 8 ball in terms of, whether it's COVID or whatever, right? We see a problem, people die, get sick, and then we're trying to figure out what the pathogen is and kind of manage it. As you'll see towards the end of my talk, when I talk about the new viruses, we're kind of trying, my lab really focuses on trying to flip that on its head a bit. And so if we can have an understanding of what types of microbes are out there in healthy ecosystems, and then when a shift happens and all of a sudden we start seeing disease, we actually have a baseline to compare to, we can easily kind of pick out these new things. So then in the early 90s, there's a report that probably a lot of you are more familiar with than I am, showing the same or similar type of wasting disease in Thalassia. And they suggested in this paper in 91 that they think it's pathogenic protist that's related to the causal agent of the eelgrass wasting disease. And so this is a little bit about Labyrinthia and this very pretty picture thanks to Cliff. It's a eukaryotic protist. It forms colonies by constructing an ectoplasmic network. And most of the labyrinthalids are actually just benign decomposers. So you can kind of think of them the way you would think of fungi in the system. And most of them are not going to cause any problems to the seagrass at all. But there are a few pathogenic strains that can be problematic. And so this is really considered an opportunistic pathogen, something that if you have kind of these co-occurring stressors that we've been hearing about all morning, that might, shift that balance from not really a problem to all of a sudden a problem for those hosts. So what you see, the long blade that's up there, you can kind of see these blackish patches on there. So pathogenic Labyrinthia can cause these necrotic patches on the seagrass tissue. And just by physically kind of cable tying two seagrass blades together, you can transmit wasting disease from one seagrass to another. And these microscope images here show the Labyrinthia within the seagrass cells, and then this is kind of the chloroplast degrading. And Cliff's lab, in conjunction with Brad Furman, who I'm guessing a lot of you guys are familiar with, and hopefully is not listening to me online rolling his eyes, have been working to continue to characterize Labyrinthia from local locations. So this is samples from Boca Ciega Bay taken earlier this month, where you can clearly see what looks like wasting disease. And they're able to culture the Labyrinthia and then look at the genetic diversity of it to see if it might be kind of a new pathogenic strain. Anytime we have disease outbreak, I think you have two things you want to think about in your head. Is this something new? So something got introduced to the area that wasn't there before, and that's why you're seeing these signs of disease. Or maybe it's something that's been there all along, but now you have changing conditions that are either favoring the pathogen or decreasing the immunity, increasing the stress of its host, and leading to a change in conditions. So basically what Cliff's lab does is they make agar plates, so typical media for growing microbes. They supplement it with hort serum. I don't know the history of that. Good question. And then they can isolate the Labyrinthia in the lab and then use molecular biology to characterize it. There's a lot that is not known about Labyrinthia prevalence and distribution, kind of here focusing on Tampa Bay. So the last study that we were aware of that we could find about Labby in Tampa Bay was more than 20 years ago. And this was mostly based on, just viewing those lesions, that necrotic tissue kind of characteristic patterns, and some microscopic evaluation. If anyone knows of stuff, kind of in that 20-year period, I wasn't here 20 years ago, I would love to hear more about it. But we have a lot of newer methods, kind of like everything molecular biology has come in and really changed a lot of these fields. And so Cliff Furman's lab has developed a quantitative PCR assay. This is kind of like not your home COVID test, but the ones that you were doing earlier on where you were sending it in. And so basically you can take a sample. They have a specific assay that's designed to target the pathogenic Labyrinthia strains. And this is important because you don't just want to know where all the Labyrinthia are, right? Like we're interested in the ones that are potential pathogens. And so they can do that, and they can go out in the environment and track not only where is it, but how high are those loads? Because it might be that it could be present at low concentrations without causing much, physical effect to the seagrass. And they've been using this technology to assess seagrass beds throughout the Keys, the Marquesas, and the Dry Tortugas, and that's some of the data that I'm going to show you on this plot. So this is one of the main figures from Duffin et al. 2021, where they looked at the prevalence, so just whether it was found or not, the Labyrinthia, and the severity in terms of the number of Labyrinthia cells per milligram of tissue with this quantitative assay. And what you see, this is kind of a blow up of this little region down here. But you can see these pies are divided, they sampled 10 individuals at each site. And so if you have, 1 out of the 10 has a color, that means only 1 out of the 10 had labyrinthia. And then the severity is the color there. So that's the Labby load in those samples. And you can see that in some of the near shore, these tended to be fresher water environments and warmer temperature. So the hot and fresh problem. They saw more labyrinthia as well as higher concentrations of it. And they were also measuring immune markers in this paper and showed that they saw less kind of activation of immune markers and suggested that it might be that the plant is putting all of its kind of energy into surviving these stressors and trying to live its life and less into protecting itself from any pathogens. Are there questions on this part that I most likely can't answer before I move on to virus? Yeah.
Is this, the labyrinthias, is it only found in shoots or do we find it in the rhizomes also?
I don't know that answer, sorry.
No, that's okay.
So it sounds like this is pretty ubiquitous around the world. So it's found because obviously you talked about Zostera. So it's common everywhere that you have seagrass pretty much.
Yeah, and as far as I'm aware, it seems like most of the problems that it's causing where you're seeing these kind of big epidemics are in Zostera, and I haven't heard as many problems in Thalassia. And I kind of have a note on this later on, but we have those Bocacia Bay samples from October. We also, in one of the sites that we're studying the viruses, just like very haphazardly picked 5 healthy looking Thalassia blades and tested them, and we found it in all 5 of them. So if I had to guess based on very, very limited amount of data, if you kind of initiated a survey for Labby in Tampa Bay, you would find it pretty widespread. And then I think there's kind of some interesting questions that could be asked there in terms of how does that correlate with the health of those beds, the physical, chemical parameters, immune markers, maybe even viruses, and maybe it is everywhere, right? But then you're only seeing it take its bad opportunistic role where the plants are more stressed. Right, into my comfort zone. Welcome to the world of viruses. So we have a recently started project that was funded by the National Science Foundation that we call VITA Seagrasses. It's viral infection dynamics among seagrasses. And this is a joint project with Dan Martin, Cliff Ross, Brad Furman, Karina Rosario, and myself. We have cool t-shirts, which is very important of any project. And what we're really looking at is viruses in seagrass I think initially I would say starting at the most basic level because there's not a lot of knowledge out there. So as a little bit of virology history, because when you hear viruses, everybody automatically thinks of COVID or the flu or something that's making us sick. But virology really initiated in plants. So that was where we kind of learned that viruses were a thing in the 1800s. And that really started with tobacco mosaic disease. So they started seeing symptoms on the leaves. And then basically through a combination of techniques figured out like, okay, well, if we filter it through this size filter, whatever that disease causing agent is still goes through the filter, right? It took a lot of time to get that down to what they essentially called a liquid poison or a contagious fluid. The science was really changing a lot back then. And one of the things that I find most interesting, I'm an optimist, so it really depresses me to just sit around and talk about viruses as killing things all day long. And one of the things I think super fascinating about plant viruses, and of course this is really all from the terrestrial world, is that a lot of the viruses are not pathogens. And so a lot of them are neutral or neutral as far as we can tell. You don't see any visible symptoms. There aren't, effects on reproduction, those sorts of things. But then there's also a bunch of viruses that have been shown to be beneficial. And so what you can see here are sort of uninfected and infected virus plants with various viruses. And then they are they help with coping with different stressors, So sometimes a plant infected with a virus will be more temperature tolerant than one without a virus. Same thing also with drought resistance. And you can see at the bottom panel, there's some really nice studies that have been done where if you have the wild type plant, it looks good, that actually has the virus in it. If you remove the virus, the plant doesn't do as well. If you reintroduce the virus, you can restore that kind of health. And so this intrigues me from the standpoint of maybe there are viruses out there that could actually help the seagrass cope with different stressors. So what do we know about aquatic plants? The answer really quickly is not very much. So there's been a ton of work done on single-celled phototrophs, so especially cyanobacteria, also single-cell eukaryotic algae, but there's very little that we know about in true plants. So in the 50s, there was one study that we could find that looked at freshwater plants, and they weren't doing anything to identify the viruses. That's fairly new technology compared to the 50s. But they were able to inoculate from the aquatic plants onto terrestrial indicator plants and show a spread of disease. And then in the 70s, people got kind of excited about it. They were like, this is a big research gap, and maybe this would be biocontrol for invasive freshwater plants. So you can think about the viruses as having many roles in these systems. In the mid-2000s, the sequencing really took off and people started doing sequence-based discovery for viruses. And there were two studies, one in 2006 and one in 2018, that identified virus sequences in Zoster marina. These are just sequences, so we don't know anything about kind of the ecological roles of these viruses, but it kind of spurred us on that this might be a potential avenue. So my lab was interested in just seeing, could we find viruses in Thalassia? We had a postdoctoral researcher, Noemi van Bogart, who was visiting from Belgium, funded by a Belgium American Education Fund grant. And we literally just went out to look. And so the initial part of this is not very systematic. And why, why are we at this stage? Why do we know so little about viruses? And it's really because they're just hard to study. They're really small. You can look at them under the microscope. It's hard to tell them apart. You need really fancy transmission electron microscope. Because they're so small, they have very little nucleic acid. It makes the sequencing hard. A lot of times we don't know the host, and so we could find a virus on a seagrass, but it might be a shrimp virus, right, or something else. And so you have to be very careful with those inferences. And then I think the biggest one is that we don't have a single test for all viruses. So if you want to look at bacterial diversity, there's one gene that's present in all bacteria. If you want to look at, human diversity, dog diversity, whatever, these things all share common genes. Viruses are all over the place. Some of them have DNA genomes, some have RNA genomes, single-stranded, double-stranded. They infect all these different things. A total pain to study. And so most of the studies will use a targeted study. So again, back to COVID, right? We have tests for coronaviruses. We can test for either SARS-CoV-2, the specific one. We can test for widely all coronaviruses. That's not going to tell you whether you have flu or not, right? So you're going to get a negative on that, and that's going to tell you yes or no, that coronavirus is there. But what if it's a norovirus? Whatever, right? So you'd have to run through thousands of different assays, and that still only works if it's a virus that's already known to us and to science. And so the technique that my lab uses is metagenomics, and to kind of put it in a fishing context, instead of targeting something with specific bait tackle, here we're just dragging a net through, and we're going to see all the viruses that are there. So this is a little bit about how the method works. We went out, collected plants, we scraped off the visible epiphytes. We tried to target young leaves just so that we didn't have as much of that epiphyte load on there, and weren't seeing as much just kind of crap that had settled there, for lack of a better word. We homogenize the seagrass blades, and then we do our best to purify the virus particles. So we kind of shake everything up, we get it all homogeneous, then we filter to remove any bacteria, anything bigger than bacteria. We treat with chloroform that disrupts membranes. We add nucleases. So at this point, we're just getting pure viruses. And then what we do is extract the RNA from that, chop it up, sequence little pieces, try to put it back together. And it's kind of like assembling a jigsaw puzzle and seeing what we find. Yeah.
Don't you, so in the purification process, don't viruses often attach themselves to bacteria? So how do you extract the virus from its host?
Yeah, so we basically put our tissue in a buffer and then put it in a bead beater, and it shakes hard. It's very disruptive. It does kind of shake everything loose. Okay. There are the most amount of viruses that are in any environment, whether it's seagrass, seawater, your gut, are bacteriophage. So they're viruses that infect the bacteria. In this case, we're actually bead beating so hard that we're also busting open the plant cells, because we want to be able to capture viruses that are not just free floating, but within there. So theoretically, we are disrupting everything. The virus particles themselves are really tough, so they don't get busted open during that process. Yeah, that's a great question. And then when we get our sequences back, there's a giant database that we compare everything to, and we're hoping we see something that looks like a virus. So we first started, and it's great actually that Ping's talk is after mine, because it turns out we're studying the same exact site, which I didn't know until one day we showed up and there were these giant so the pyramids there. I was like, what the heck are those? So we sampled right at the South Skyway here, so like right at the southern end of the Skyway Bridge, and we just went there really quickly. It was someplace we could access from shore, go out, collect some plants, and we studied 4 locations initially. And I'm just putting this up here so it'll make sense when I talk about N1 through N4 later. We got really lucky. So we took a few plants from site N1. It was about 10 plants to start with. We weren't even taking the whole plants. We were just taking like this much of the blades. Again, everything we targeted looked completely healthy. So we weren't necessarily trying to find disease. We did a really small amount of sequencing. Generally, my lab generates like millions of sequences from a sample. We generated 96. This was an unfunded project. It was highly exploratory. It was like, let's just see how it goes. We were able to detect a virus. It's called turtlegrass virus X, because that's kind of the nomenclature that people in this field go by, is to name it after its host. This is the genome structure for anybody who really cares about viral genomes, but I have a feeling I might be the only one in this room. What I think is really interesting about this virus, in addition to the fact that it's the first virus known in Thalassia, is that it's related to viruses known in land plants. So if you think about it from an evolutionary perspective, I think there's a lot we have to learn here. It's about 66% identical, which is not that, it's not that identical. So related, but weakly related to foxtail mosaic virus, so viruses that infect land grasses. And it's not more, I'll show you a very neat slide at the end that suggests there may be a seagrass specific clade of these viruses, but initially it wasn't like vastly different from the terrestrial ones. Another really interesting thing about this is it had really limited geographic distribution. So the samples we sequenced from were from site N1. I don't know if you can see the scale here, but this is about 5 meters. So these sites are maybe 10 meters apart. Like this is very localized. So once we found the virus, we could design one of those specific tests, like the one I was saying for SARS-CoV-2, right? We designed a very specific test for that virus. We went back and we sampled lots of individuals at these 4 sites. So about 60 to 80% of the blades at N1 were positive. At N2, we saw it in maybe 10 to 20% of them. We never detected it at N3 or N4. And so it's very heterogeneous on the small scale. We again developed a quantitative PCR assay, and we see a lot of it. So there's up to 1 billion copies of this virus per milligram of seagrass tissue. So when it's present, it's there, a lot of it. In general, we only did this for like in 2 seasons, but in general, the viral load was higher in the summer than the winter, and this is something that we're going to be doing in the upcoming grant that just started. We've now detected this virus at this site for over 7 years, and so if it's causing overt problems, we're certainly not seeing them. This is a mixed bed. In fact, it seems like Syringodium is kind of taking over this bed. It's getting a little harder to find Thalassia there. We haven't found it in any of the co-occurring seagrass species there, even when they're physically like right at site N1. And interestingly, we do detect the virus in flowers and fruit. We were hoping to do more of that this past summer, and like either they didn't flower or we completely missed it. I'm not sure.
We think it happened really early this year.
For very similar things, because we would like to test, is it in the pollen or like trying to get at the mechanisms.
I went out multiple times and I must have just been too late.
Okay, that was our experience too, but I've heard it anecdotally that it wasn't just us. And then again, this is that same site where we just collected a few random individuals to test for Labyrinthia and also found that. So in more systematic surveys moving forward, we're going to test for Labyrinthia and for the virus. In each of the samples, we're also looking at genotype, which I'll get into in a second, just to try to like really understand biology here, but also keep in mind there could be lots of other viruses. We have a ton of questions, and I apologize for the text-heavy slide, but this is basically what our grant proposal focuses on. So the first thing is what determines or limits the distribution of this virus within the meadow. So could that be host genotype? Maybe some of the seagrass are susceptible to virus infection, others are not. Initially, I can say I don't think that's what's going on, even though we put a lot of eggs in that basket. So, the data tell you the truth. And specifically, can some of the genotypes limit, are they resistant to the virus, either not be able to be infected by it or just control the viral loads, while others have high viral loads but limited damage from it. And then also, what are the ecological impacts? And this is where I think we need to go, and this is why I'm excited to kind of talk with this group. So are there neutral, positive, or negative interactions? We're going to be setting up mesocosm experiments where we're going to test under normal conditions as well as hypo and hypersalinity to see as stressors, to see if we see any differences in kind of fate, survival, health of the seagrass when they're infected versus not infected. This is taking quite a bit of method development because there are no methods for how to infect a seagrass with a virus. So we're doing a lot of things like trying to just adapt the terrestrial virus methods to seagrass. And I'm hoping we'll get lucky. So just as a little update, before I only told you about these 4 sites, N1 through N4, we've now set up, now that we have a little funding, we've set up kind of a systematic survey at this site. So this is the Skyway site. And what you see everywhere there's a dot is somewhere that we sampled. If it's a blue dot, it just means there wasn't any seagrass when we dove down at that point. Everywhere that's red is positive for the virus. Yellow is negative for the virus. Orange is like a weak positive. There's only a few of those. We haven't applied the quantitative methods to this yet, but basically you can see that it's extremely patchy. So N1 and N2, which were kind of mostly positive, do have positives right around it. We have some definite negative areas. We don't see it very much close to shore, which I think is interesting. We've now done genotyping on these seagrasses and are working up that data, which is new to me and a bit of a nightmare. So if anyone loves that stuff, please come talk to me. But to see if there's any correlations between the genotype of the seagrass and the virus. We are also trying to maintain the seagrass in the lab, which is going surprisingly well so far. And I've done a couple initial things where we're definitely noting that TVX concentrations are higher in the roots than they are in the blades of the plants. So we see it in roots, rhizomes, and in the blades, but concentrations are highest in the roots. That's actually consistent with what this group of viruses does in terrestrial plants. We're developing experimental virus transmission methods, including last week we had an accidental transmission. So this suggests it's going to work out, which is we had brought back 6 plants from a nearshore site where we so far haven't seen the virus. We put them in aquaria together. We tested them right away, but it takes a little while to get that data back. In the meantime, they sat in an aquarium together. Then it turned out 1 out of the 6 did have the virus. And then we tested them again about a week later, and now all 6 of them have the virus. And so I think this is actually positive for our study. Still doesn't explain to me why that's not happening in the field, right? Because they're all there. So this is all very preliminary. I'm not sure I trust it yet, but I think this is a great group to bounce ideas off of.
Stuff to think about.
Exactly. And we're also working right now when we do the infection, we don't have this virus in culture. So the only way to do this is to take, the blade, homogenize it, purify the viruses, and add those to another seagrass. There could be other viruses there, right, in addition to this one. And so one of the things we're doing is kind of building an infectious clone of this virus so we can do more controlled experiments. In the future, in conjunction with Cliffs Lab, they're going to be doing these mesocosm experiments. We'll be looking at the cellular responses, changes in gene expression upon infection. If we see immune responses like hydrogen peroxide, oxidative bursts, things like that, and photochemical efficiency with infection. And the last thing that I want to mention, and I'll definitely get with Sheila after this meeting, but also if this is useful to anyone in any other context. So originally we just found the turtlegrass virus X. It has this really limited distribution. So then we said, could we detect broader group, right? So back to the COVID example. Now, instead of just detecting SARS-CoV-2, can we detect all coronaviruses and do a bigger survey? And Jean Lim in my lab has successfully created kind of universal Potex virus primers. So these get the terrestrial ones and all the seagrass ones that we know so far. This kind of yellow shaded box is all of those. I'm unsure about the rupia. That was where we did find it initially. We couldn't find it again. Yeah, and that might be a red herring at this point, but we've certainly found it. We found it now in the Panhandle. We found it at Lansing Park. We found them down at Bush Key. And then we actually have 2 groups, which I think is interesting from our site. So that original map that I showed you that had a lot of negatives, we went back to all the samples and we tested them with these broader primers. And we found that a lot of the sites that were negative for the turtlegrass virus X are positive for a variant of this virus. So it's about 80% identical. It's related, but it's definitely not the same. So we'll also be looking at co-infection. Maybe that's something that limits the distribution if you have one virus that you're resistant to the related. And that's all I've got. Happy to take questions.
So I was thinking back to your question about the patchy nature of that distribution. It seems rather odd, especially since what you saw in the lab kind of confirms that it's contagious. But then I started thinking about the clonal nature of seagrass in general, and then I wonder if what you're looking at is maybe it's not as contagious in the field, but you're actually sampling, parts of the same whole, so to speak.
Yeah, I think that's a really important question, and we don't know. The rhizomes at this site are pretty deep, plus we don't want to go screw up the whole bed by digging things out. I promise we're being very and so I think that's really a reasonable possibility. So we've now sequenced 9 or looked at 9 microsatellite markers. I don't have those results for you yet, but I'm hoping that will kind of help shore that up. It could be it's only in one clone and that clone's, weaves throughout that site. In which case, then I think the question is, are the other ones resistant to it for some reason, whether that's genetically or due to co-occurring members of the virome or the microbiome? Lots of questions. We also repeated, I don't have the results yet, but we repeated that same survey that we did in August 2022, in August 2023 from the same sites. And so it'll be very interesting to see, how reproducible are those patterns.
We kind of came to Maya because we had seen some big seagrass die-offs in areas, and then we were also kind of noticing changes in losses in certain species. So we just kind of wanted to talk to her about from that loss and pathogen perspective. But then we also are really interested in this component that's related to, can you make seagrass more resilient in some way, shape, or form? And so I know Sheila's presented some of her master's thesis work too about, whether or not there's a potential to enhance the resilience of some of our seagrass meadows by understanding the nature of whether or not how they're reproducing and some of those dynamics. So we're also thinking about ways that we can enhance the adaptive capacity of seagrass resources in Tampa Bay. So there's a lot of folks that are investing now in transplanting, and transplanting has been an activity that's listed in the CCMP for a long time. But we're trying to be more strategic and thoughtful because, again, what do we do about it? So, okay, we've got a virus. What do we do? What's the action? Or if we understand the genetic and reproductive kind of components, is there something we do with that, or is it just now we know this cool thing?
But that's always a risk when you don't know what it's doing either, right? The nightmares are that the media is oh my God, seagrass found or virus found in seagrass throughout Tampa Bay to cover the microphone, right? But we don't know that this is a problem, so maybe it's beneficial, maybe it's not, maybe it's nothing right now. I think there's also and this would be way far downstream. We're nowhere near this part, but what people have done with this group of viruses and other groups of viruses is also develop them as vectors for gene silencing and stuff. So more genetic manipulation, right? And I think this becomes relevant thinking down a restoration angle is, if you know that expression of this one pathway is hurting the seagrass under some conditions, or they maybe have a stress response that you'd like to upregulate, we now have a virus that naturally infects these cells that we could potentially modify to tell the plant to do what we want. Again, that's long-term, right? But I think it gives you hopefully the rationale for why it's worth it to go out there and look at seagrass viruses.
Yeah, it's so interesting. I'm thinking about my own body, and you said, your gut bacteria, and I am an individual and nobody else has my individual viruses and bacteria in myself. And maybe that's a somewhat similar to seagrasses, that we kind of think of them all as genus species, but it's even maybe, you know, more kind of minute than that, that we have this, you know, more diversity in the virus bacteria found in seagrasses equals more resilience, you know, overall.
And certainly in
So
corals, that's
cool.
an avenue that's being pursued a lot. You know, so one advantage of microbes is that they replicate much faster than a eukaryote, or, you know, than a seagrass in this case, or a coral. And so the thought is, if you can figure out what are kind of the good types of bacteria, same way that, you know, we eat yogurt and probiotics, right, have that kind of, people are coming aboard to that idea. But if you kind of know, like, what are the good bacteria that you would want your seagrass to have in order to be resilient, you could actually try to manipulate or try to select for those, and that might help them. You know, with corals, we know certain bacteria or certain zooxanthellae can help them adapt to climate or to temperature. I'll just keep it at temperature, to rising temperatures, you know, more quickly. And so I think kind of considering what the microbiome of these seagrasses are is very important.
Marcus, and then we got to move on to the next.
Yeah, I'm sorry.
Yeah, you mentioned future work. You were thinking about mesocosm studies. Have you considered using temperature and/or salinity as other treatments in those?
Yeah, so we're definitely planning on using salinity. So we're going to do kind of baseline salinity for the site, and then higher and lower. We hadn't talked, well, I don't want to say we hadn't talked about temperature. We decided temperature was harder to control in the facilities that we were using. But if you have thoughts about it, I'd love to talk about that as well.
Not especially. I'm just thinking in the context of these comorbidities or other stressors, and obviously for your work the context is virology, but it could lend other insights into how it's affecting seagrasses as a whole.
Yeah, absolutely.
And you can agitate the sediment in the bottom to test King's theory that it's wave agitated.
Stitch together the connective thread for like how I
sneaky job then.
We connect all these topics. So I talked to you about some of, you know, not just the 3 successive mapping periods you lost, but I'm really glad you're here, Roger, because one of the other things Roger is calling everyone's attention to is there in the wintertime in downtown St. Petersburg, we've seen large, significant piles of seagrass rack washing up. And so what's causing all of that seagrass to slough off during that wintertime period? And so we've got, so you know, is something killing it? You know, is it a virus? That was one of our questions. And then the other is it, you know, wave and wind action? And so we know we see cold fronts come through in that wintertime period. And we also know that we see, we had the operation of commercial vessels, like the ferry is back and it's operating right out of there near that North Shore seagrass bed. And that's been a topic of conversation in the Nitrogen Management Consortium, is what role is the shipping activity playing to these environmentally sensitive areas? We know we see that a lot, those impacts a lot in the Hillsborough Bay segment, which is also experiencing seagrass loss. And in some of those areas where we're seeing seagrass loss in Middle Tampa Bay as well. So at a future TAC meeting, I think we'll probably be inviting Steve to come back and talk about some work that we've been partnering with Steve and Mark and their crew to look at wave sensors, which, you know, they've presented on some work in the past, but we're also getting ready to launch something specifically looking at North Shore and the ferry wakes and how to also evaluate how that might be related to wind-driven wave action as well. So keep an eye out for that. But we've also seen in the wake of some of the stresses that you get from the wind and wave energy, a move, particularly from the state of Florida, to be fortifying causeways. We saw that after Hurricane Ian took out the causeway down at Sanibel Island, and as a result, there's been significant resilience investment in fortifying these causeways at all of the bridges. There's a big effort right now looking at the Courtney Campbell and how they can fortify those sections of causeway. And this project at the Sunshine Skyway is another example, one that you probably have seen, had questions about, had people ask you about, all of those things. So Ping's here to tell you that he didn't just let them put it in, he's also gonna test how they work. So he'll tell you a little bit about that project and what they're finding so far. And again, you only just put the stuff in, you're just starting the monitoring program. So it's another one of these instances of, we don't have all the answers, it's early phase work. So Ping?
Yeah. I'm pretty loud, I can just talk here. That's okay. Well, something much simpler and hopefully happier than viruses. WAS talk, and so WAS stands for Wave Attenuation Device, that was developed by a company called Living Shoreline Solutions. And these are my team. None of us are part of that company. But for me, I have worked with the Living Shorelines company for about 20 years now. And all of a sudden, there is a lot of interest, a lot of installations of these artificial reef systems, with WAS being one of them. Axel, Michael, co-author Libby, Sophia, and are here. And so quick overall, the study area, quickly. A study area and a quick overview of the design of the WAS system, the factors to consider, installations and photos of the installation. As Maya said, this just went in, and we did a post-construction monitoring, specifically focusing on the Hurricane Idalia's forcing and some summary. So we're at the same site. Maya did her seagrass sampling, and so for us, we're looking at the physical forcing. And the site is exposed to waves coming out of the open Gulf, and also the wind coming out of this westerly direction, south-southwest and northwest-west, have a rather large fetch, so it's capable of generating considerable wave. Therefore, this side, we need to consider both Gulf of Mexico wave swells coming in, and locally generated wave should be considered in the design. So these are just examples of some wave model runs that we did, the design, like the layout and the orientation and so on and so forth. But I'm not getting into the details. A few points I'm trying to make here is, so the wave can come out of the north and it can come out of the south, the storm waves. These are big waves. And we use at the mouth of Tampa Bay, so the northerly incident wave, southerly wave get blocked pretty effectively by these landforms at the bay. And the westerly wave obviously can come through a lot more efficiently. So this is just to look at how the ocean wave, Gulf of Mexico, we call it ocean, coming in, and how well it can get to the project site. However, and because this area, we have all these landforms, wind play a pretty significant role. I just threw a 14 meter per second wave, which is about 30 miles an hour. Just the westerly wind, the westerly wind will have the longest fetch. So we'll make bigger waves out here. These are just examples showing the factors that we need to consider in kind of assessing the upper limit for the design. So we have a 30 mile an hour wind coming out of west, and you'll see the wave will be much bigger. This for the northerly, southerly ocean wave, and the westerly ocean wave will have the biggest wave. Then what if I had a 1 meter surge? Right, that'll make the water deeper out here. So this locally wind generated wave, and Steve also may have the information, is a pretty strong function of water depth. If the water is deeper, then you can generate bigger waves. Water is shallower, you don't generate bigger wave, but the wave forcing is a very strong function of water depth. That's my question of the hurricane and the seagrass, is that the wave moves like this, like oscillatory motion. It's a very strong function of water depth. When water is deeper, when you dive, you go down, you don't feel wave forcing. And when the water is shallow, you get down 2-3 meters, you kind of rock and rolling with the back and forth wave motion. So water depth is important forcing. That'll come in play later. So we ran all bunch of alternatives, and there are all these different designs that I proposed, and this is the one, how do I put this? This is the one the DOT was able to get through. Yeah, well, there is no gap, right? We have two long ones. There is one almost 1,600 feet, another one 1,230 feet. Usually we would have gaps. People call it manatee passes. So we did have design. I did propose the one with manatee gap, but of course when you have gap, when the structure is so close to shoreline, the wave can come through and get to the shoreline effectively. So if you have continuous, they can protect this shoreline better. So I had nothing to do with the permitting and everything. So
All your response.
yeah, we have all the alternatives. They were able to get this one through. So, so some photos of the installation. To my knowledge, these are one of the biggest, if not the biggest, artificial reefs that's been put out there. And so there are two sizes was used: 8.5 feet or 2.6 meters, at 10.5 feet and 3.2 meters. These are the most that they did, and so they're very large. And recently, there has been quite a few. This wave attenuation device installed. Most of them are about 5 to 6 feet. 5 feet is the one they use the most. So this is almost double the size. And those reef balls tends to be smaller. So these are really big ones. Now there are some questions that's related to the bigger units. These are just some photos. Oh, why is it moving? This is just photos installation, pretty impressive. And so they have a barge, and then they have this unit. They just drop this thing in, and this is the company that invented this artificial reef system. Again, I have nothing to do with this company. I've been working with them as a consultant. So this is Dean Drivers. He has a lot of experience installing this. The company that's installing this is not this company. So he's out there kind of supervise, provide them with the experience on how to position them. And they can have a boat like this to push it around a little bit to make sure they put it in the exact position. And they have all these PVC pipes marking I call them the array of this. And if you see the boat is trying to pushing it to the right position. And so the thing was constructed somewhere over here. Everybody goes over Sunshine Sky, we see this big pile of concrete. And so at the end of the day, it looked like this. Right? At the end of the day, it looked like this when it's installed. And on the ground or in the water, it kind of looked like this. And and right after the installation, we got Hurricane Idalia. So fortunate for us living in Tampa Bay area, and the hurricane was relatively far from us. And it's a medium size and wasn't really moving as fast or slow. So it's like a medium sized hurricane, pretty strong, and also move at a medium speed. Not really slow like Ian or really fast like Charlie. However, it did generate a fairly energetic condition. The Tampa Bay area, fortunately, we're pretty well monitored in terms of tides and wave and winds and so on and so forth. And so we use the tide gauge at SMP. So the surge that is generated by Idalia is pretty impressive, right? It's 1.49, the highest surge water level that relative to mean sea level. Highest that ever measured in the 70-some years of SMP is 1.54. So we're only about this much from the maximum surge that was measured at SMP. Actually, at our other project site at McKay Bay, Idalia generated the highest surge that's measured by however long these gauges have been installed. And we also have a wave gauge that's offshore Egmont Key, and we measured upward to about 5 meters, just short of 5 meters. I should point out the gauge is at 12-meter depth, so 5-meter wave is pretty much the upper limit you can measure, because it's become limited by the water depth. The wave should be start breaking right there. So the point is, while Idalia did generate very energetic conditions in terms of surge within the bay, and very energetic conditions in terms of wave outside Tampa Bay. So, but our study site is within the Tampa Bay. So we established a wave model, try to propagate this offshore wave into the area. So this is the offshore wave, and our study site, the wave obviously is very well protected by the bay itself. This is without the wind. So my point is, wind is actually pretty significant. So we added the measured wind somewhere over here onto this model. Again, still much, much lower than the offshore wave, of course, because the mouth is blocking. It also has to do with the direction of the wave. The Idalia wave coming out of a southwest, like south-southwest angle, and the landforms at the mouth is pretty effective in blocking it. And also the wind tends to be south-southwest. And as I said earlier, the westerly wind is the most effective in making big waves, right? So at one point, that's what this box is. At one point during the passage of the storm, we did have a south-southwest or westerly wind, but by then the velocity of the wind, the speed of wind has slowed down. However, it still generated big wave. So in this graph, I took out the offshore wave so I can have the scale a little bit better. So the blue is the wave that's, this is model, right? Computed with no wind. So the grain, the darker grain or gray is the wave that has the wind. So the wind, basically wind forcing basically double the wave height. So at the end of the day, we had a wave of about 0.9 meters or 3 feet. Just to do some thought experiments to see what would be the maximum forcing that we may have at this particular site. So I just, for the fun of it, Olivia did most of the modeling. We just put a westerly wind that has the longest fed. We put a westerly wind, 18 meters per second is at the lower threshold of a tropical storm. So that would generate about 0.94 meter, 9 meter wave, which is similar to the maximum wave that is generated by Idalia. So what if I put a hurricane strength wind? So this is the lower boundary of hurricane, 75 miles an hour or 34 meters per second. Then it can get upward to 1.4 meter at the site. So this is actually the upper limit when we did the design. So to cap this, Idalia did generate energetic condition, but not the very high condition that is possible. However, I would argue the probability of this is pretty small, because if you look at the hurricane movement, they come from the south. Usually you don't have the strongest sustained wind coming out of south. Usually west, usually be south, southwest, or in the track of Irma, you may have east, northeast. So this may not be very often or frequent. However, it is possible. I didn't really look at what the possibility is. And so that's the background. So we did the monitoring. We took a lot of photos before and after the storm. I tried to take some underwater photos, and none of my photo comes as nice as the photos that have been shown. Because the water, I blame the water. The water is not as clear. And we did a post-Idalia survey, because this is only a month after. We are mostly looking at the scour of the units, also because these are very large units. There's a lot of questions about the settlement, the scour, the stability, and so that's what we're looking at. And so just some photos, right? So some photos, it would answer most of the questions that I listed earlier, but I do have data. So that's before, that's after, at the end. So we focus, I started at the end. At the end, they performed really well, partly because they put ripraps at the end. So I was also involved in the very first one at Sunken Island. some kind of bird island when we first put down, and putting riprap kind of at one more turn. I did suggest that they should think of it, but at one more turn, you have to get the rock and blah, blah, blah. So they didn't do riprap at Sunken Island. Some of end unit really tipped, and I think one or two even fell. So learn from that, and the bases have ripraps, so you can see before and after, they're holding pretty well. And this one is got another end out here. And so again, they have riprap at the end. And this one I took off the bridge. So it's the angle is a little weird. So look, the outside row is seems to be considerably lower than the inside row. We did measure this elevation difference is part of the angle of the photo. So now we look at this end again before and after, and you can see the riprap, and so the unit stands pretty well. And then the other end over here, also the units stand pretty well. And so then we also took a lot of photo in the middle, right? This section don't have a riprap, and you know, one of the advantage of many of these artificial reef system is the small footprint. So if we put riprap around the entire unit, then you kind of lose the advantage of the smaller footprint. So that was not part. I just suggested to them that they shouldn't put riprap around it, and I don't think they have it over there. So in the middle part, some of the unit kind of tilted a little bit. So this is the worst case. I zoomed in. This is the worst looking ones. However, from again, this thing is called wave attenuation device. The goal is to dissipate wave energy, and because it tilted a little bit, its functioning of dissipating wave energy is not influenced at all. However, DOT wanted them to string them up, so I kind of sent an email. I think they decided not to level it. I have some data to explain why. Again, this little tilting didn't really influence the performance of a wave attenuation. So that's a photo taken from the water. It looks pretty sweet and everything. And I have some underwater photo. They're not very good. So this is the riprap at the end. This is the riprap at the end, and the fishes really like to swim in and out of those holes. You know, again, this photo is not for the fish. It's for this. I'm looking at the scour at the edge to see how the units would handle wave, and a lot of the engineers tends to think this thing will just sink into the substrate, which is not really not this substrate. If it's really, really soft mud, maybe. However, in this area, when you have wave, the wave forcing can be very strong. It's usually the scour around the units. So trying to document the scour. Obviously, when you see the sand look like this compared to this, that means that there's some fresh movement of sand or erosion. And just photos again. So this looking for the erosion, try to see if the units is buried into the sand or it gets scoured out, the edge got exposed. I did see some that the edge got exposed a little bit. So this is like a scour, I call it, because although only a few weeks in, there's stuff growing on it, and if you see a really clean concrete color, I figure maybe that's the scour, and that's a starfish scale, so it's not too significant. And sometimes the edge gets scoured out, the edge gets scoured. However, most of them, this is on the landward side. The seaward side, the water is just too murky. I didn't have any air, so by the time I get down, try to aim my camera, and I ran out of air. And but the outside, on that day, it looks that it's still mostly in the sand. So we did a survey, and that's Kendall on top of the units, and that's me swimming. And so this is actually at a high tide with a little surge. This is considerably high. You know, spring high tide is not even here. And we're trying to go out on a low tide, It turns out we couldn't find a low tide. It turns out high tide is easier because I can swim out there at high tide. At low tide, the gap is much smaller. I would not be able to squeeze out. This, I can just swim out of there. So we did a lot of data, collected a lot of data, total of 530 points. And we ran 4 cross sections across the unit and 1 control line, another 4 cross sections and 1 control line. We also took a whole bunch of points on top of the units and also at the base, just to see the elevation and the elevation change that give us a quantitative measure of tilting or settling and so on and so forth. So this is basically part of the, we took almost over 250 points on top of these units. On top of these units, that is the design elevation. That's the design elevation at 3 feet above mean sea level, or 2.6 feet above NAVD. And so this is all the average. Again, the blue line is sorted. So this has nothing to do with the space. Just want to look at what is the lowest and what is the highest out of these 250 measurements in comparison with the design elevation. So overall, the average top is 2.3, and so it's about 0.3 feet below the design elevation. So if I draw a conclusion on settlement, there hasn't really been a whole lot of settlement. By the way, the settlement over here is mostly sand. It's pretty hard. And when I started to put the rock down, always poke around a little. It hit the bottom hard. It's not going. So, and then we figure, well, you have the inside row, then you have the outside row. So the blue is the inside row, they're close to land. The green is outside row. This makes sense, right? The outside row is a little lower than the inside row. Again, in comparison with the design elevation. And the settlement is minor. Even the outside row is only 10 centimeters below, on average, below the designed elevation. So these are the transects and that we surveyed from land to sea. For example, this P1 is over here, and I'm only going to focus out of here. So we do see some scour on the seaward end and some scour on the landward side. So it's usually the scour on the seaward side or the bay side is a little bit bigger, deeper than the outside. I should point out, although the scour hole, if I measure from here to the top, is 0.5 meter, but it's not all scour. So basically, this gets scoured, then this sand get moved right seaward of it, form a little pile. So in terms of if I extend this bed out, follow the trend, the scour, the net scour may be just 10, 20 centimeters. Then you have the deposition. So this kind of deposition, you do see them for reprep, kind of a rubber mount breakwater also, right? Because the way it breaks out here, the scour underneath is what typically happens. And the control line, this one is not very good because it's right next to that inlet, so it's much deeper than that. And so that's the same 3 and 4 similar pattern, scour on the landward side, scour on the seaward side. And so for this one, we're doing this one. This one, I decided to take those rods out just to look at the scour hole, the scour around the installation area. So it's like this, and then extend about 6-7 meters. 6-7 meters. The deepest you can get about 0.5 meter. Again, this scour is a bunch of this, a good amount of this elevation increases because of deposition and not exactly scour. So these over here, these are the bigger units, right? These are the 3-meter units. And I should point out, for example, these ones, you can see the landward is a little higher than the seaward. The landward is a little higher than the seaward. So this is for me to make sure my survey is reasonable. If we get a weird number, maybe we didn't hold the stick straight enough, right? Or Sophia was taking the shot when the stick wasn't stable. So we don't have any of those. Or we get rid of those weird ones. We didn't have many weird ones. But Anyhow, so that's kind of get me to the summary. It's only a short term. And the focus is really to see the stability, because these are bigger units. There's that are being used more and more, and there's many pushes to kind of use them in a higher energy environment with this closer to the mouth of Tampa Bay, and would be one of the environment. So they have two sections, about 500 meters or 1,600 feet, pretty long, right? Almost 400 meters, 1,200 feet. The two rows was usually they do two rows because this thing is a pyramid shape. So the first row and the second row, they're kind of overlapped. The unit on the seaward row will overlap the gap on the landward row. So if you look through, there's always something blocking the wave coming in, although there are gaps, but they are offset. And so it was designed at 3 feet above mean sea level. The 3 feet is almost the same elevation at the seawall. The seawall is about this much higher than the top of the WAS. That was the reason of designing this. I figure there's not a whole lot of reason to have it above the existing seawall. Idalia generated energetic condition within the bay, and so the Gulf of Mexico wave, as well as the locally wind-generated wave, contributed equally, actually, almost half-half for the case based on the wave model. And the significant wave height reached about 0.9 meters and 3 feet. I should point out the model is a spectrum model, so this is significant wave height, and the model did consider, a higher wave in the RAN. So overall, the units holds quite well during Idalia with a very minor tilting. Scour ditch was measured about upward to 0.5 meters, was measured on the seaward side as expected, nothing kind of unexpected or excessive. And overall, the units was 0.3 feet lower than the design elevation. I must say they did a good job installing it. They were really very meticulous, making sure you're putting in the location and like shake it. I didn't know if they shake. They said they shake it so that they get to the elevation. So they did a good job, and so it's fairly stable. If I just take the top elevation for all the units, the lowest is 0.49, or about a foot below the design elevation. The highest is 0.87, or about 0.2 to 3 feet, about 9 centimeters above the design elevation. So that's all I have. We'll monitor more, but I mostly on the physical side. I don't know what's their ecological goal, or creating some seagrass landward or something. I don't know, but I'm focusing on the physical side of things.
Any questions for Ping?
I've got a quick one. Dr. Wang, we worked together years ago. You remember EG?
Yeah, Siemens. Yeah, I do.
Would you say that, have there been post-studies at EG Simmons
I actually
Park,
have, yeah, I
to
did.
thwart erosion over there? And do you think they're effective?
I did. I actually have another presentation. I did that. I talked them into the monitoring. I did a survey, and we did a survey in April, and we did another survey after Idalia at EG Siemens, similar photos like this for stability, and they actually did help gain some sediment. So it helped.
Understand. I still think they couldn't.
I know. I just don't remember. By the way, it's a long time ago.
And it's just an observation. They seem to be proactive. My question about Idalia, or for that matter, any storm going offshore in the Gulf of Mexico, it sounded as if the winds were predominantly southerly, and would there not be a westerly direction with the passage of that storm north of Tampa Bay because it's counterclockwise?
Yeah, so the westerly wind would come when the storm passes us.
Yes.
Usually when it passes us, the wave kind of tends to subside a little. However, that is a possibility. Another thing I should point out, I didn't have time. Actually, the scour, once again, I said the wave forcing is a very strong function of water depth. So when you have a surge and the wave forcing is actually significantly decreased, Actually, for the EG Siemens, when they were installing, it was winter time, there was this cold front coming through, the whole area is exposed, and they actually had quite some scour along the seaward edge during installation, just because of cold front and low water level, so the waves hitting on it. And they kind of fixed it. And I went over there, they fixed it, and it has been standing. I have lots of, I can give you the kind of thing I have. But I think a future study for this would be maybe during a cold front when the water level is depressed, although the wave forcing, the oscillatory motion is a function of water depth log functions. It increases very fast in shallower water, although the wave can be smaller. And then we may go see the scour or the scour hole evolve during a winter cold front.
I'm sure there'll also be interest in how fish are using those and whether or not they're creating a protective environment for seagrasses to fill in even further.
That's for somebody here.
I know that.
So I understand they are not fixed. They are over something, but not fixed in position. So if there is, I don't know, a strong current or something, can they move?
How much do they weigh? Because that would be.
They weigh a lot.
Yeah.
They weigh, for these ones, I think they're like, they claim, I did the calculation, they're like 15, 20 tons. They don't look that heavy, they're very heavy. Although that's the weight in the air. The weight in the water is half that. So the weight in the water is half that. And because I'm involved with this guy for a long time, and do they move? Actually, in this kind of substrate we have here, they didn't. They did try some, because it has artificial reef, they did try some in Playa del Carmen, the Cancun. They put it on the hard bottom just to dissipate wave and making reefs. And when you put on the hard bottom, they do move. And they are kind of submerged, but that's like in the open.
We're not gonna do that. We're not gonna do that here.
This one did not move.
Couple of quick announcements. There's either for discussion. The proposed meeting schedule for next year for TAC meetings. So it's listed here on the agenda, and I'll be putting it on the TBEP calendar so you can add it as an event to your calendars. But take a look at those, and if there's anything that's a conflict with those dates that I should be aware of before I finalize everything, please let me know. I also just wanted to call your attention to, we're going to send out a survey to our committees, the TAC and the subcommittees as well, just to make sure that those subcommittees are all necessary, meeting at the frequency that works for everybody, in a format that works for you all, and in a way that is, helping you all conduct your work as part of our management conference. So keep an eye out for that, and please take the time to respond to that survey when you see it. Then the only other thing that I wanted to share with you all was, some of you in the room might know him and some may not, but Dr. Gabe Vargo passed last Wednesday. Gabe was really instrumental in helping to establish the management targets related to the light environment and the chlorophyll A response for our program. He's also done a lot of work. He's really well-known and influential in the birding community at Boyd Hill. He helped to set up the Bird of Prey program in the Friends of Boyd Hill. And so it's truly a loss for our community, but wanted to make sure that you all were aware that he passed last Wednesday. There's not going to be a service or anything like that, but somebody that was really foundational and important to our work. So I just wanted to acknowledge that as well. Any announcements, things y'all want to share, things we need to discuss? Anne.
So the Florida Ornithological Society is going to be meeting at Boyd Hill on November 10 through 12, and people are invited to participate.
You.
Can I ask a question? This is a Julie question. I'm so sorry for everybody in this group, but you are also smart. And this is not my topic, but artificial intelligence, AI is in media, it's in other science disciplines, and do we, kind of the environmental side of the world, are we, like, how do we expect that tool to help us and this, I wrote it down on Marcus's presentation, but it's a tool that is not just a smart brain to kind of combine all of our realms of expertise into a body of knowledge, but then also might be able to help ask questions that humans are not necessarily asking. Like, where are we in that front? AI in science moving forward, and it's not necessarily answerable. I just have been thinking about it more and more as it's available, it's out there.
Marcus, do you wanna weigh in some of that?
Big questions, yeah.
Big question.
The community, our community is thinking a lot about AI right now, and not just how we can leverage it, but what are the pitfalls? Because there's a lot. As an example, I asked an image generator to create a picture of seagrass in Tampa Bay for me, and it was horrible. So it's not going to give you the right answer, nor should it. Well, it should, but it doesn't have the capability to give you the right answer. And we're, as a program, I could just speak for the SRA program, we're trying to think about how we can kind of get ahead of that so that we have established boundaries or a box within which we're working. Because frankly, we are using it, the SRA program, right now. Personally, I use it to help with coding tasks, like things that would take a lot of time but not a lot of brain power. I can automate a lot of simple processes to free myself up. But and other things too, like distillation of tech reports for like simple plain language summaries. There's ways we can use it in that capacity, but in any way we're using it, there's always that human backstop to it, doorstop to it.
Yeah, I
It
don't
says
think
this is BS, this is not. That still needs to be there.
For now, but I think isn't AI kind of a toddler? And, you know, when does it become an adult? And what time are we like looking at?
I think what's changed about AI is the accessibility of it now to people, and that's what's kind of promising, but also is terrifying. Anybody can use it, and the best way I've seen, I don't know the answer to you know when it's become mature enough, but I've heard it described as like the best intern you've ever had.
Yeah.
It will be the most productive thing that will be at your disposal, but it might churn out garbage. So all I can say is thinking about these things, but also just always proofread, check it, make sure it's giving you the things that you expect. It might give you something that seems to work, seems to be right, but it can give you the wrong answer for a lot of different reasons. And it's up to us with our like collective knowledge of, you know, we're the experts on these things, so we need to fact check it. But understand that it could be a tool. Just verify what it's giving you. What Maya is showing is our attempt at defining that box for the program. This is in our data management SOP that we wrote 2 or 3 years ago, and we just added this section about how we're using it, and this is us trying to get in front of top-down control of these tools to say, don't use it, basically.
I mean, just ChatGPT is very specific for like literature or,
It's useful for code. I mean, I think Marcus talked about at the Open Science Subcommittee, how he can help use it to translate old SAS code, for example, into our code that we can then wrap into our open science framework. And you can actually use it for a lot of things. And there are these other tools. So, you know, when Marcus was developing this language, we talked about like how Chat PDF is one where you could feed it our whole tech report library and our CCNP, for example, and you could train an AI agent on the technical stuff that we've produced that's in the gray literature and maybe is not as findable. And so there's utility to that if it has these sort of protective backstops that Marcus is talking about. So we kind of spell out our policy or our thoughts and expect this to evolve over time. Mm-hmm. This is something that the other NEPs, the other national estuary programs are talking about as well, and they have sort of different levels of use and comfort with the ones that are housed in universities tend to have more of the kind of approach that looks like ours, which is thinking about like how you can use it appropriately and what are the backstops to, leverage it, but in an ethical and defensible way for the science that we're producing. I know Dave Tomasco's online, and I think in the chat, he's making a point that we've actually been using AI for decades in our models and how we process data. It's just not quite at the same level of accessibility like y'all were talking about. So we have more powerful computing, and some of these large language models have evolved to these different points. But I would, if St. Pete or other organizations that you're involved with are thinking about these things, this is one resource, and we can continue to, like I said, make this is up there on our GitHub and available for everybody to look at. And if you have comments or suggestions about things you think we can incorporate, or if you can use it in a data policy of your own, we'd encourage you to do so. We're trying to be a little bit like forward thinking on these things. Chris, did you have your hand up?
Yeah, I just wanted to, so that's something that we're very much looking at. I don't know if you would classify it as AI because it's such a big term, but we've been looking at using semi-automated machine learning for our seagrass maps. We did a pretty thorough side-by-side comparison in 2018, and in 2020, we were kind of ready to make the shift and go to a more semi-automated approach. But then we started seeing real losses in seagrass, so we didn't really want to move away from the more manual photo interpreter model. But our intent is to continue to transition, and we have actually started implementing that. We started back in 2020 as a first cut. So we let the machine generate the map, and it generates thousands of little polygons, and then the photo interpreter goes in. So to that analogy of toddler versus adult, we're kind of in that maybe infant stage, but certainly the opportunity, I think, will present itself in the very near future to kind of transition into a more AI-based mapping convention, with the emphasis being on the word semi, because I think at least in the foreseeable future, you're still going to need a human photo interpreter to verify what that output is. So it's quasi right now. And along those lines, just as an announcement, we are gearing up for our next round of seagrass mapping. Our flight window opens on December 1st, so we're looking forward to getting up in the air and starting to acquire the imagery. This year is one of the years where we do the entire district coast, so we'll be mapping the Suncoast estuaries from Tampa Bay, Clearwater Harbor, St. Joseph Sound down to Charlotte Harbor. But we're also going to be mapping the Springs Coast region as well. And that goes roughly from Tarpon Springs north to Wakasasa Bay, just near Cedar Key, out to about 25 miles offshore. So.
I think I'm good.
Gary?
I just wanted to make people aware if they want to join us for the Habitat Restoration Consortium. That's actually going to be in person in December for our last meeting of the year. So that's on December 6th at the St. Pete STEM Center. So put that on your calendars. There'll also be an email notice going out about that tomorrow.
And if you haven't grabbed a copy of the basis proceedings, there's plenty up there. We have plenty more at the office, so take some for your friends, great Christmas presents, whatever. Also, people online, if you haven't got a copy, we can possibly arrange.
All right, see y'all in January. Thanks.
Oh my goodness. He was awesome.